If you could sit in a ship that never needed fuel, never broke down, and never got tired, what would it actually feel like to leave the Milky Way and try to visit galaxy in the universe? On paper, it sounds simple. Point the nose toward deep space and go. But the moment you zoom out from our little corner of the cosmos, the scale stops feeling like distance and starts feeling like a different category of reality. Most of us imagine galaxies as crowded neighbors, bright swirls sitting almost shoulder to shoulder out there. In truth, each one is more like an island floating in a dark ocean so wide that even light takes millions of years to cross it. And that's before we even talk about the fact that the universe isn't just sitting still, it's stretching, fast. There are galaxies we'll never reach, not because we're too slow, but because the space between us and them is expanding faster than any ship could ever chase. So instead of treating this like a fantasy road trip, let's take the idea seriously. What would a journey like this demand? What parts of the cosmos would actually be accessible? And what would you see if you could sweep through galaxy after galaxy, watching how the universe changes as you move? Let's break the whole thing down and see what flying through every galaxy really means. First, there are a lot of galaxies. For the part of the universe we can observe, current estimates suggest there are as many as 2 trillion galaxies. That's far more than their earlier conventional estimate of 100 to 200 billion. The jump comes from deeper surveys and updated models that account for many faint, small galaxies our telescopes historically couldn't pick up. To get a sense of how thorough that is, earlier counts were based on deep field images from a tiny sliver of sky, then extrapolated. The new estimate injects a dose of humility. Most galaxies in the observable universe are too faint or too distant for us to have seen yet. Now, 2 trillion sounds like you could at least hypothetically tour them all, but here's where cosmic geography hits hard. On average, if galaxies were distributed uniformly, and they're not, but bear with me, each one would be separated by an enormous swath of mostly empty space. Space between galaxies is vast. For example, even the nearest large galaxy to us, Andromeda Galaxy, is about 2.5 million light-years away. That's the distance light travels in 2.5 million years. The majority of galaxies, though, are far farther. Because of how diluted galaxies are across space, if you imagine flying from one to the next, you are almost always flying through near-empty intergalactic space. Vast voids. If galaxies were evenly spaced, they aren't exactly, each could be considered to have its own territory of many cubic light-years, an enormous cosmic desert between points of light. Even more challenging, the universe itself is expanding. On very large scales, space between distant galaxies stretches, so some galaxies are moving away from us and from each other faster than light can travel through that space. That doesn't violate relativity because it's space itself expanding, but it does mean that certain galaxies are forever out of reach, even given infinite time or a perfect light-speed spaceship. In fact, many cosmologists estimate that the majority of galaxies, perhaps over 90% of all existing ones, are already receding beyond the cosmic horizon, unreachable, now or ever. The upshot: even though there are trillions of galaxies out there, the sheer emptiness between them and the accelerating expansion of space mean that the dream of visiting every galaxy isn't just practically hard. It's physically impossible under known physics. So yes, the universe may be packed with galaxies, but it's also overwhelmingly empty and growing more so over cosmic time. Before we talk about traveling between galaxies at any speed, there's a basic question that trips people up. What universe are we even talking about? When someone says every galaxy in the universe, they usually imagine a single bounded thing, like an enormous sphere full of stars and dark patches. But cosmology works differently. There's the observable universe, which is the part we can actually see or measure, and then there's the entire universe, which could be far larger. Maybe infinite, maybe curved in ways we don't fully grasp yet. And those two ideas lead to very different expectations about what flying through galaxies even means. The observable universe is defined by one constraint. Light has had only 13.8 billion years to reach us since the Big Bang. That sets a maximum distance for what we can detect. By the time you factor in the expansion of space, the radius of the observable universe is roughly 46 billion light-years. That's not because anything traveled faster than light, it's because while the light was traveling, the space it moved through stretched. So the photons reaching us today come from regions that are now far away. If you picture this properly, the observable universe isn't a sphere with Earth at the center because we're special. It's centered on us simply because we're observing from here. Any other observer anywhere else would see their own observable sphere centered around them. This alone creates a strange consequence. No one anywhere gets to see the whole universe. Everyone only sees the part of the universe close enough and old enough to have had time to send them light. It also leads to a quiet but important truth. The observable universe is not the universe, and the gap between those two sets grows bigger the farther you imagine flying. Let's say you are in a hypothetical ship that can cruise at almost the speed of light. You point it toward the edge of the observable universe. What do you find when you cross that edge? Not a boundary, not a wall, not an outside. You find more universe, more galaxies, more empty regions, more everything. The edge isn't physical, it's informational. It only marks the limit of what has had time to reach us. So if your ship somehow kept going, you'd be inside a region never seen by any telescope, but it wouldn't feel different. Your surroundings would look like typical deep space, distant galaxies ahead, faint structures shaped by dark matter, the glow of background radiation if you have the sensors to pick it up. And here's the twist. Even if you keep moving outward for billions of years, the observable universe from your viewpoint keeps resetting around you. You always carry your own horizon. But the entire universe, whatever its actual size, remains far beyond anything you can reach. Even traveling forever at light speed doesn't give you access to all of it. This difference becomes even more dramatic when you factor in cosmic expansion. In 1998, astronomers discovered that the expansion of the universe isn't slowing down, it's speeding up. This acceleration is driven by something we call dark energy. We don't know what it is, but we can measure its effects. And one of the most important effects is that regions of the universe far enough away are receding from us faster than light. They aren't moving through space that quickly. The space itself between us and them is stretching. But for travel, the outcome is the same. Those regions are unreachable. So even if the entire universe were finite, and there's no evidence it is, you would still not be able to reach all of it. Not even close. The acceleration fences off vast expanses of space. Any galaxies farther than a certain distance, about 16 billion light-years away today, are already permanently beyond reach. That distance gets smaller the farther into the future we go. It's easy to gloss over what that means, but it matters deeply for the idea of visiting galaxies. If the observable universe contains roughly 2 trillion galaxies, the entire universe may contain many times more, maybe 100 times more, maybe infinitely more. But the fraction that could ever be reachable by any civilization, no matter how advanced, shrink over time. Eventually, only the galaxies gravitationally bound to ours will remain accessible. Everything else drifts farther and farther away. The whole thing gets even stranger when you consider that what we observe today is not what exists right now. Every galaxy we see is shown to us at some point in its past. The more distant it is, the younger it appears. When we view a galaxy 10 billion light-years away, we're seeing it as it looked 10 billion years ago. If you could somehow travel there, it wouldn't look like the image you saw from Earth. It would be older, maybe more developed, maybe merging with neighbors, maybe a different shape entirely. This time-lagged view means something subtle but important. The observable universe is also a time boundary, not just a distance boundary. When you look outward, you're looking backward in time. If you travel outward, you're entering regions that were visible only in an earlier state. But you can never see what they look like right now, because right now is different everywhere, and information about those changes hasn't had time to reach you. So when people imagine flying through every galaxy, they usually picture a giant static map where each galaxy is a fixed stop you can visit. The reality is closer to trying to visit every city on Earth, while the continents drift apart. Countries appear and disappear, and the atmosphere expands. Everything you aim for is changing while you move toward it. Some destinations are dissolving behind you, and many are sprinting away faster than you can chase them. Even this doesn't fully convey the weirdness. Consider this thought experiment. Imagine you start flying outward at near-light speed today. For the first few billion years of travel, the observable universe from your ship keeps growing in the direction you're moving. More galaxies come into view as the light from them finally catches up to you. You're seeing parts of the universe Earth will never see because you're closer to them and their light has a shorter distance to travel. But at the same time, the distant regions behind you are being swallowed by the accelerating expansion. The universe isn't static while you're on your journey. You're not sweeping across a fixed landscape. You're surfing through a dynamic environment where the cosmic horizon shifts around you. New galaxies appear, others vanish beyond reach, and the entire structure stretches underneath your path. You're moving inside a constantly changing bubble of visibility. This raises a deeper question. If the universe may be infinite, does every galaxy even mean anything? Infinity doesn't behave like a really large number. You can't finish an infinite task, even with infinite time. Traveling forever at light speed would not give you access to infinite galaxies. You would only ever explore a limited region whose boundaries are set by cosmic expansion, not by your engine. And that brings us to one of the most counterintuitive insights in cosmology. The universe used to be more reachable than it is now. Right after the Big Bang, everything was closer because space hadn't expanded as much. As billions of years passed, galaxies spread out, clusters drifted apart, and the horizon of what's reachable shrank. In the very distant future, almost all galaxies will fade behind the cosmic expansion and vanish from view forever. Only our local group, Andromeda, the Milky Way, and a handful of smaller galaxies will remain. For a traveler, that shrinking horizon means something profound. If you could fly through the universe billions of years ago, you could reach more galaxies than you could today. If you try the same trip billions of years in the future, your options would be far fewer. Exploration is a race against cosmic expansion. Even hypothetical civilizations that thrive for trillions of years might be trapped in isolated pockets of the universe, not because they lack technology, but because the universe itself limits what is possible. But this doesn't make the idea of traveling between galaxies useless. It just reframes it. You're not moving through a giant static arena. You're navigating a landscape shaped by physics, time, and expansion. And every part of that landscape tells us something about what the universe is and how it works. For example, the fact that the observable universe shows galaxies at different stages of development lets us piece together cosmic history. We can see young galaxies at great distances, older galaxies closer in, and everything in between. It's like looking through a stack of historical photographs, except they're arranged spatially instead of chronologically. That natural layering is one reason we know how galaxies evolve. It's why we know that early galaxies were smaller and more chaotic. It's why we can see the rate of star formation rise and fall over billions of years. And flying through these different regions, in theory, is like walking through a museum where each room is a different age of the universe. But the catch is that the museum is collapsing behind you and expanding ahead of you while you walk. The layout is shifting, the walls are moving, and some hallways disappear as you get close to them. The story remains, but the structure constantly rearranges itself. Another important point: the observable universe has been growing. The longer the universe exists, the more light has time to reach us from distant sources. So a traveler in the future would be able to see slightly farther than we can today, but only up to a point. Because of accelerating expansion, there's a cosmic limit you can never cross. Eventually, the growth of the observable universe slows and stops. Then it reverses. Distant galaxies start to disappear from view, one by one. This means the universe we see today is the largest it will ever appear. We're living at a kind of cosmic sweet spot. Billions of years from now, distant galaxies will no longer be visible. The night sky will look emptier. Even the cosmic microwave background, the faint glow left over from the Big Bang, will fade. So if you imagine flying through the universe millions or billions of years from now, you're navigating a very different place. The scenery changes. The targets change. In a practical sense, the universe becomes lonelier. All of this reshapes how we think about travel. The dream of flying through every galaxy starts to look less like a grand tour and more like an exploration bounded by physics. You can explore your region. You can explore the galaxies close enough for light to outrun the expansion. You can see deeper into the past the farther you go, but you never get access to the entire universe. You never could. No one could. Understanding that difference, observable versus entire, doesn't kill the fantasy. It just anchors it. It gives us a real map with real rules. And within that map, even a small slice of the universe is unimaginably rich. You don't need every galaxy for the journey to matter. Even a tiny reachable fraction holds more stars, planets and stories than any civilization could ever exhaust. When people picture the universe, they usually imagine something crowded. Maybe they've seen those Hubble deep field images where the frame is jam-packed with galaxies, spirals, ellipses, distorted arcs from gravitational lensing. It's easy to get the impression that space is dense with structures. But those images are deceptive in the same way aerial night photos of Earth are deceptive. You see all the city lights, but you don't see the deserts or oceans. You see brightness, not emptiness. If you could pause the universe and measure the average distances between galaxies, you'd find something that feels almost comically mismatched compared to our mental picture. Galaxies are enormous, tens of thousands to hundreds of thousands of light years across, but they're separated by distances measured in millions of light years. It's like taking islands the size of continents and spreading them across an ocean so wide that the islands are invisible to one another unless you have incredibly sensitive equipment. To make this a little more concrete, the Milky Way is about 100,000 light-years across. That's the diameter of the disk where most of our stars live. The nearest large galaxy, Andromeda, is roughly 2.5 million light-years away. If you shrank the Milky Way to the size of a dinner plate, Andromeda would be another dinner plate located about 25 meters down a hallway. And that hallway is pitch black, almost empty, and filled mostly with sparse particles of gas and dark matter you'd never notice unless you were looking for them with scientific instruments. But even that analogy is tame compared to the larger stretches of empty space. The universe isn't laid out in a neat, uniform grid. Galaxies bunch together into clusters. Clusters link into filaments. Filaments surround enormous voids, regions where there might be almost nothing at all except the occasional lonely galaxy drifting through an ocean of darkness. Some voids are hundreds of millions of light years across. These are not small gaps, they are the dominant terrain of the universe. This uneven structure is what cosmologists call the cosmic web. Imagine something like a three-dimensional spider web, but with strands so faint that if you could stand inside it, you wouldn't see anything. On the nodes of the web, where strands intersect, you get massive galaxy clusters with thousands of galaxies. Along the strands, you get smaller clusters and filaments. And inside the gaps, vast regions many times bigger than clusters, you get almost nothing. Now, picture flying through this. For long stretches, you're not weaving through star systems or hopping from galaxy to galaxy. You're navigating tremendous deserts where you might not encounter anything significant for millions or tens of millions of years. A galaxy every few million light years might not sound too sparse, but when you remember that light itself needs millions of years to cross those distances, you get a sense of scale that's totally incompatible with the usual sci-fi galaxy hopping fantasy. Even the idea of between galaxies is misleading. Within a galaxy, stars are relatively close, on the order of a few light years apart in typical regions and closer in dense cores. That means that if your ship could do, say, 1% of the speed of light, you could reach the nearest stars in a few hundred years. Still long for a human lifetime, but not unimaginable for a multi-generation mission or a robotic probe. But once you leave the galaxy, you leave behind that scale. Crossing 2.5 million light years to visit Andromeda becomes a completely different category of journey. At 1% the speed of light, it would take you 250 million years. That's older than almost every species on Earth today. At half the speed of light, an impossible speed for anything with mass using known physics, it would still take 5 million years. You are not dealing with travel times, you're dealing with geological time, evolutionary time, time long enough that continents shift, climates transform, and species appear and disappear. Now extend that thought to the idea of visiting multiple galaxies. The nearest dozen large galaxies belong to the same general region of space, the local group. These galaxies are gravitationally bound. That means that the expansion of the universe doesn't push them away from us. Gravity is strong enough on this scale to hold them together. The Milky Way, Andromeda, and a collection of smaller galaxies form this local island of stability in a universe that's otherwise pulling itself apart. Beyond the local group is the Virgo cluster, the nearest major cluster. It's about 54 million light-years away. Again, imagine how far that is. Light takes 54 million years to get from there to here. Dinosaurs dominated Earth when that light began its trip. A ship traveling at the speed of light itself would get there no sooner than that. A ship traveling at any fraction of light speed would take longer, thousands, millions, or tens of millions of years more. And if you zoom out further, you get the Laniakea supercluster, a truly massive region where gravity binds together tens of thousands of galaxies. But even this home region is just a single part of the larger cosmic web. Filaments stretch outward, connecting superclusters across hundreds of millions of light years. Between those filaments lie voids, so barren that crossing from one side to the other at light speed could take hundreds of millions of years. Once you understand the cosmic web, you understand something fundamental about the dream of visiting galaxies. It's not just that they're far apart, it's that the space between them is unimaginably bigger than they are. Each galaxy is like a bright metropolis surrounded by a practically infinite night. You don't hop between them. You commit to enormous journeys where the emptiness defines the experience more than the destinations. Another detail often overlooked is the medium between galaxies. It's not truly empty. There's the intergalactic medium, the tenuous gas, stray atoms, cosmic rays, and dark matter. It's so thin that in a cubic meter you might have a few atoms, but over millions of light years, even that matters. Cosmic rays are constant. High-energy particles zip across the universe at near light speed, capable of damaging electronics and biology if unshielded. Collisions with dust, rare but dangerous, become catastrophic at high speeds. Space is dark, but it is not benign. Traveling through the intergalactic medium at significant fractions of light speed would require shielding that borders on unrealistic with current physics. Even a grain of sand at those speeds would have the energy of a bomb. And the higher you push toward light speed, the more violent even tiny collisions become. This isn't a reason that travel is impossible. It's simply a reminder that the environment between galaxies is harsh in ways the vacuum of interplanetary space is not. Another subtlety is that galaxies themselves evolve over time. Spiral galaxies like the Milky Way can merge and transform into elliptical galaxies. Star formation changes. Black holes grow. Gas gets consumed. Structures warp. When you look out across space, you're seeing galaxies at different points in their life cycles because of the time light takes to reach you. If you could somehow travel across them, you wouldn't be visiting a static gallery of cosmic art. You'd be touring a sequence of changing, aging, transforming systems. The galaxy you saw from a distance will not be the galaxy you arrive at millions of years later. Consider galaxy clusters. These regions have thousands of galaxies orbiting in a gravitational well created mostly by dark matter. The distances between galaxies inside a cluster are smaller than the distances between isolated field galaxies. Still huge, but compared to the cosmic average, clusters are relatively dense. If you were flying through a rich cluster like Virgo or Coma, you'd encounter galaxies more regularly. The sky around you might show dozens of bright cores instead of a few faint smudges. That cluster environment is the closest thing in the universe to what people imagine when they picture a crowded cosmos. But even there, crowded is a bit misleading. Stars inside galaxies are still far apart. Galaxies inside clusters might pass within a few 100,000 light years of each other. That's close on cosmic scales, but it's still trillions of times farther than anything within the Milky Way. A cluster feels more alive, more dynamic, but it's still built on distances that are too large to grasp intuitively. This means that even an idealized journey where you visit every galaxy would mostly be a journey through nothingness. You'd have long periods, millions of years, where your surroundings barely change. The occasional smudge of a distant galaxy might shift. Maybe you'd see the faint glow of intra-cluster light if you're passing near a dense region. But most of the time, there's no sense of motion the way we experience it on Earth. There's no wind, no background reference points, just the black. This emptiness works both for and against travel. On the one hand, the lack of obstacles is convenient. You're not dodging stars or threading asteroid belts. Most of the journey is open space. On the other hand, the isolation magnifies the scale. When everything looks the same for millions of years, you lose the comforting illusion that you're getting anywhere. It's like crossing an ocean where the horizon always looks identical no matter how far you've come. One useful analogy is this. Imagine the entire observable universe is the size of Earth. On that scale, the Milky Way would be a single bacterium. The nearest galaxy would be another bacterium, located a few centimeters away. And the space between them would be mostly ocean. The cosmic web on this scale would be subtle, tiny clusters of bacteria connected by faint strands, with vast clear oceans between them. Trying to visit every galaxy on that Earth-sized ocean would be like instructing a microscopic ship to visit every bacterium floating anywhere in the global sea. The number isn't the problem. The spacing is. And this spacing gets stretched by cosmic expansion. The farther apart galaxies are, the faster the space between them expands. This means some galaxies are effectively being swept away from us by the current of the expanding cosmos. No matter how fast you travel, short of breaking the laws of physics, you will never catch up. They're already receding faster than light relative to us because the space between us grows faster than light can bridge it. This doesn't apply to galaxies in our gravitationally bound local group or cluster, but it applies to almost everything else farther out. So not only are galaxies staggeringly far apart, many of them are actively getting farther, and the rate of that separation increases with distance. A traveler trying to visit every galaxy finds the target list shrinking over time. Galaxies that were once in reach drift out of reach forever. For the galaxies that are reachable, their spacing is still so immense that even hypothetical travel close to light speed barely dents the time needed. If you want a sense of how undefeated these distances are, consider this. Light itself, the fastest thing in the universe, would take billions of years to cross the observable universe. Nothing can outrun light, so nothing can survey everything, even in principle. In practice, if some future civilization did attempt intergalactic travel, they wouldn't aim for every galaxy. They'd aim for the closest cluster, maybe the next. They might send self-replicating probes that spread outward over millions of years, hopping from galaxy to galaxy at whatever pace is physically doable. Over absurdly long epochs, maybe they could visit thousands of galaxies. But the 2 trillion in the observable universe? Not possible. And the unobservable ones? Even less so. When you absorb all this, a surprising idea emerges. The universe isn't structured for visiting, it's structured for observing. You can learn about everything from where you are because light comes to you, but you can't physically reach most of it. Observation is how we explore the universe. Travel is how we explore our neighborhood. And that neighborhood is already immense beyond comprehension. Before you can even imagine steering a ship from one galaxy to another, you have to deal with the biggest rule in the universe. Nothing can move through space faster than light. That limit alone makes intergalactic travel brutally slow. But the real problem isn't speed. It's the way the universe itself behaves. Space isn't just a stage where everything sits, it stretches. And because of that stretching, most galaxies are already beyond any possible journey, no matter what engine you build or how long you travel. This idea sounds abstract, but it's actually one of the simplest truths in modern cosmology. The universe has been expanding ever since the Big Bang. In the early 20th century, astronomers discovered that distant galaxies are moving away from us. The farther a galaxy is, the faster it's receding. For nearby galaxies, that motion can be explained by their actual movement through space, kind of like cars driving away from you on a road. But once you get far enough out, the speeds become too large to make sense as normal motion. Galaxies appear to be moving away faster than light. That's where the key insight comes in. Distant galaxies aren't speeding through space faster than light. The space between us and them is expanding, and on large enough scales, that expansion outpaces the speed of light. This doesn't violate any physical laws because relativity only forbids objects from moving through space faster than light. It doesn't say anything about how fast space itself can grow. If you picture space as a stretchy fabric, you can imagine little coins glued onto the surface. The coins don't change size, but the fabric stretches, increasing the distance between them. If the fabric stretches fast enough, 2 coins can end up separating faster than any ant could crawl across the fabric. It's not the coins doing the moving, it's the fabric. That's the universe. Galaxies gravitationally bound to one another stay together, like coins glued tightly to the same part of the fabric. But galaxies far apart drift away as the fabric of space expands between them. Once they're far enough, the expansion becomes so fast that even light emitted toward us will never reach us. Those galaxies might as well be gone. There's a name for this boundary, the cosmic event horizon. It's the distance beyond which events can never influence us, even if the universe lasts forever. In other words, the horizon marks the set of galaxies that are permanently unreachable. Not unreachable for humans, unreachable for physics. Right now, that horizon lies at around 16 billion light-years away. The observable universe, by comparison, has a radius of about 46 billion light-years. That means most of what we can see is already beyond the horizon. We see the light they emitted long ago, but their current selves are now too far away for any signal to reach us. If you launched a beam of light toward them today, it would never catch up. If you launched a ship today, the result would be the same. This creates a strange but important divide. There are galaxies we can see but will never visit. There are galaxies we can see but will eventually stop seeing because their light will no longer reach us. And there are galaxies we can neither see nor visit, regions so far away that their light has not and will never arrive. To put it plainly, the overwhelming majority of galaxies in the universe, well over 90%, are permanently unreachable. They are not part of our cosmic future, they are part of our cosmic past. We see only the ancient versions of them, and that's all we'll ever get. Even stranger, the number of reachable galaxies shrinks over time. The horizon isn't a fixed boundary. As dark energy drives the accelerated expansion, more and more galaxies slip past it. 1 trillion years from now, the only galaxies left in view will be the ones gravitationally bound to us today. Everything else will fade into the cosmic darkness, leaving future observers with the false impression that the universe is small and empty. This shrinking future is one of the most dramatic consequences of dark energy. We live at a special moment in cosmic history, special not because humans are unique, but because this is the era when galaxies are still visible. We arrive just in time to see the universe before it pulls itself apart. From the perspective of exploration, this is a vanishing opportunity. Cosmic expansion sets the limits of a journey before you ever leave home. To see how dramatic the effect is, imagine a perfectly idealized spaceship. No mass issues, no engine limits, capable of reaching 99.999% of the speed of light. Even such a ship is helpless in the face of cosmic expansion. Traveling to a galaxy already beyond the horizon is like trying to swim upstream in a river flowing faster than you can swim. It doesn't matter how strong you are, the river wins. And there's another twist. Even galaxies that are inside the horizon might not be reachable if you leave too late. The universe is not constant. It changes as you move through it. Expansion accelerates over time, so a galaxy that is within reach today might cross the horizon millions or billions of years from now. If you launch a ship too late, the ship never arrives. Timing matters in the universe. If a civilization wanted to visit distant galaxies, or simply wanted to send a probe, they would have to launch early before those galaxies drifted too far away. This places a surprising constraint on intergalactic exploration. The universe itself has deadlines. But even if a civilization mastered near-light-speed travel, the list of possible destinations is still short. The only galaxies that are definitely reachable are the ones in our local group: the Milky Way, Andromeda, Triangulum, and a few dozen small dwarf galaxies. These systems are gravitational companions. Expansion cannot separate them because their mutual gravity holds them together tightly enough to resist the stretch of space. Beyond the local group lies the Virgo cluster, and beyond that, the larger Virgo supercluster, all the way up to the vast structures of the Laniakea supercluster. Within this region, gravity still has some influence, but not enough to bind the entire thing permanently. That means some galaxies in those regions might be reachable, and some might not, depending on where the horizon sits over time. It's possible that a fast enough spaceship launched soon enough could reach parts of Virgo or even farther along the local filament. But it's not possible to reach all of it. The cosmic expansion continues pulling parts of the supercluster away. The farther out you look, the less promise there is. To understand just how quickly things slip into the unreachable zone, imagine this timeline. Today, we can see 2 trillion galaxies. A few billion years from now, most galaxies beyond the local group leave our horizon. Tens of billions of years from now, only the local group remains visible. Hundreds of billions of years from now, even the cosmic microwave background fades. The universe begins to look like a dark bubble of isolated galaxies. If you imagine a civilization living in that far future, they will never know the cosmic web existed. They will never see the vast expanse we see today. Their night sky will be a local cluster and nothing else. They would have no idea the universe was once full of trillions of galaxies. They might even conclude, incorrectly, that the universe is static and small. This future isolation explains why theoretical astrophysicists sometimes talk about a cosmic archive, a concept where advanced civilizations might want to record as much information as possible before the universe becomes observationally starved. If you want to understand the cosmos, this era, now, and the billions of years around now, is the only window where you can. For travelers, this shrinking horizon has emotional weight. If you dream of flying through the universe, the truth is bittersweet. You live at the only time when the universe is visible enough to inspire that dream, but governed by physics, strict enough to keep the dream out of reach. But that doesn't mean intergalactic travel is pointless, it just reframes the scale. The galaxies that are reachable, even if only a handful, are still enormous. And they're close enough that a civilization with advanced propulsion could, in principle, travel between them over long stretches of time. In the very distant future, the Milky Way and Andromeda will merge into a single galaxy, sometimes called Milkdromeda. That galaxy will be home to trillions of stars. With enough time and enough technology, even a tiny pocket of the universe contains more than enough to explore. Another detail often overlooked is that time dilation helps long-distance travelers. If you travel near the speed of light, time slows down for you relative to the outside universe. You could cross millions of light years while only experiencing thousands of years on your ship. From your perspective, intergalactic travel becomes almost practical. But when you arrive, the universe outside may be millions of years older. The galaxy you're heading toward will have aged dramatically. Its stars will have shifted. Its structure will have evolved. And if you're aiming at a galaxy near the edge of today's horizon, it might not even be reachable by the time you get close. Time dilation solves the personal travel time problem, but it does nothing to solve the horizon problem. You still can't reach galaxies beyond the boundary. Relativity gives you ways to stretch your subjective experience of time, but it doesn't give you ways to outrun the expansion of the universe. This limitation shapes almost everything about cosmic travel. It tells you what's possible and what's fantasy. It tells you which journeys are worth planning and which targets are mirages. And it forces you to see the universe as a living system, not a static star map, but a dynamic structure with moving walls. If you step back from the technical details, something poetic emerges from this, even though we're avoiding poetic phrasing. The universe has a built-in horizon, not to frustrate explorers, but because expansion is part of its nature. The cosmos evolves, structures shift, distances change. The dream of flying through galaxies doesn't collide with scientific laws. It reveals them. And once you know those laws, the universe feels bigger, not smaller. You realize that the tiny region we can reach consists of dozens of galaxies, each with hundreds of billions of stars. You don't need every galaxy to have a lifetime of exploration. Even a single galaxy is more than you could ever finish. If you've ever wondered what it would be like to travel between galaxies at enormous speeds, the first thing to understand is that your sense of time wouldn't match the universe's sense of time. Relativity makes long-distance travel strange in a way nothing else does. Even without breaking any laws of physics, you can experience a journey that feels manageable while the outside universe ages by millions of years. To make sense of this, start simple. In everyday life, time feels fixed. A second is a second. An hour is an hour. You don't experience time differently by walking faster or driving a car. But once your speed becomes a significant fraction of the speed of light, time stops behaving the way your intuition expects. Your internal clock keeps ticking normally for you, but relative to the outside world, your clock runs slow. Your ship ages less than the universe around it. The effect is tiny at everyday speeds, but it grows rapidly as you push closer to the speed of light. At half the speed of light, the dilation is noticeable but mild. At 90%, it becomes significant. At 99%, it's dramatic, and by the time you reach 99.999% of the speed of light, time can slow so drastically that entire millions of years flow by outside while you might only experience decades. This is not science fiction. It's built into the math of special relativity. The closer your speed is to light speed, the greater the factor by which your time slows relative to the rest of the universe. But before imagining radical shortcuts across the cosmos, you have to understand a catch. Reaching such speeds requires staggering amounts of energy. And once you're moving that fast, slowing down requires equally staggering energy. It's not like stepping on a brake pedal. At near-light speed, simply turning becomes a force that could crush anything not engineered to withstand incredible stresses. And every atom you collide with hits your ship with tremendous energy, enough to damage or destroy your craft if you don't have extraordinary shielding. Let's start with the experience inside the ship. Suppose you're cruising at 99.99% of the speed of light. From your point of view, everything inside the ship feels normal. Your heart beats the same way. You age at your usual rate. Your surroundings look stable. But the universe outside transforms. Distances in the direction you're traveling become compressed due to length contraction, another effect predicted by relativity. Galaxies that would normally be millions of light years away appear significantly closer in your frame of reference. It's not an illusion. It's a consequence of how space and time warp for objects moving at high speeds. The stars ahead of you also appear to shift in color. Light from the direction you're moving gets blue shifted. Its wavelength shortens. Visible light might push into ultraviolet or even X-ray territory if your speed is extreme enough. Meanwhile, light from behind you gets red shifted, stretched out into longer wavelengths. This means the sky literally changes color depending on your speed and direction. Another strange consequence is that more of the universe crowds into the small patch of sky in front of you. Relativistic aberration compresses the view. When you accelerate to near light speed, your field of view narrows like a tunnel. The universe appears to rush toward you from a bright, compressed region. The rest of the sky fades toward darkness. This isn't a special effect, it's how the geometry of space-time presents itself at those velocities. At first glance, this makes intergalactic travel seem easier, with length contraction reducing distances and time dilation, reducing subjective travel times. A journey of millions of light years might feel short to the traveler. But relativity never gives you something for free. The benefits come with complications. For one, while you can experience a relatively short trip, you can't avoid the fact that the universe outside continues aging. If you make a journey that takes 40 years on your ship but spans 10 million light years, the galaxy you left behind will experience 10 million years of history during your absence. Civilizations rise and fall. Stars are born and die. Planetary systems shift or get disrupted. The home you return to isn't the home you left. In fact, it might not exist at all. This leads to a paradoxical truth. Even if intergalactic travel becomes possible for travelers, it might still be impractical for societies. You can leave, but you can't return to anything familiar. The trip becomes a one-way leap into a future that moves on without you. A civilization could send explorers, but it couldn't expect to interact with them again in any meaningful time frame. Communication lags would be absurdly long. Updates from the ship would reach home millions of years later. Now let's consider energy. Pushing anything with mass close to light speed requires huge amounts of energy. The closer you get, the more your effective inertia grows. This is why no object with mass can actually reach or surpass light speed. The energy needed approaches infinity, so even if you can reach 99.999% of light speed, that last fraction is impossibly expensive. You can get close enough to feel the effects of relativity strongly, but you can't cheat the limit. This makes propulsion one of the biggest bottlenecks in intergalactic travel. Chemical rockets? Not even close. Nuclear propulsion? Helpful for interplanetary scales. Useless for galaxy hopping. Matter-antimatter reactions? They get you much farther since they're one of the most energy-dense reactions possible. But even antimatter isn't enough to accelerate a large crewed ship to extreme fractions of light speed without fuel masses larger than entire planets. One of the only propulsion ideas that sidesteps the fuel issue is a light sail or laser sail, using giant lasers or sunlight to push a reflective sail across vast distances. The benefit is that you don't carry your fuel with you. The drawback is that you need incredible infrastructure, lasers the size of cities or larger stable systems, powering them for years or decades, and a sail capable of surviving intense radiation pressure without tearing apart. And even then, slowing down at the destination becomes a new problem. You'd need a second array of lasers waiting for you, positioned in the target galaxy, an impossible requirement unless previous missions have already traveled there. Another twist: the faster you go, the more dangerous even ordinary particles become. A single hydrogen atom striking your hull at relativistic speeds delivers enough energy to cause radiation bursts. Multiply that by the density of interstellar or intergalactic space, and you get a constant stream of high-energy impacts. With enough shielding and enough engineering, a ship might survive. But the shielding itself becomes heavy, and heavy ships are harder to accelerate. Everything fights everything else. Also, at these speeds, time dilation helps you but hurts your environment. Cosmic rays, the high-energy particles that fly through space, would become even more energetic as they hit your ship head-on. The same blue shifting effect that changes starlight also affects cosmic radiation. What might be a harmless background particle could arrive as a lethal one. In some extreme scenarios, the front of your ship would need shielding thick enough to blunt a constant barrage of micro-collisions, any of which could destabilize electronics or injure passengers. Inside the ship, if it's designed correctly, you wouldn't feel any of this directly. The environment could be made as comfortable as any Earth habitat, but outside, the universe is a violent place for anything moving at relativistic speeds. It's not like flying through air, it's like flying through a storm of invisible bullets and radiation blasts. That's why theoretical designs for near-light-speed craft often involve long, needle-shaped ships with massive shielding in the front and delicate components buried deep inside. Now let's imagine the psychological experience. If you're traveling near light speed, your perception of the outside world is compressed into a small, bright cone. You would see galaxies ahead of you, distorted and brightened. The ones behind you stretch and fade. If you rotated the ship or peered through instruments, you could get a sense of the wider sky, but motion itself distorts what your eyes receive. The universe becomes directional. Up, down, left, right. Those concepts lose meaning. The journey becomes a tunnel forward through a cosmos that bends around your speed. And then there's the time you spend coasting between galaxies. Even with massive time dilation, the journey still feels long to you, possibly years or decades. Inside the ship, daily life would continue. People would age, routines would form. But outside, millions or tens of millions of years might pass. When you arrive, the galaxy you aimed for doesn't match the one you saw when you left. Galaxies evolve over cosmic time. Star formation rates change. Collisions reshape spirals into ellipses. Black holes merge. Systems drift. Even if you aimed perfectly, the target galaxy would have moved, stretched, rotated, and changed by the time you arrived. The only way to navigate successfully is to constantly update your trajectory based on information from thousands or millions of years ago. That's like steering a boat using weather reports from the age of dinosaurs. This doesn't make the journey impossible, just strange. Navigation becomes prediction, not reaction. You aim at where a galaxy will be in millions of years, not where it is now. If you wanted to return home, relativity complicates that too. You'd need to accelerate again, turn your ship around, and endure the same effects in reverse. By the time you got back, millions more years would have passed at home. The Milky Way itself might have merged with Andromeda. Entire star systems could be gone. You could return to a galaxy that barely resembles the one you left. If a civilization tried to maintain communication, the delays would make it impossible. A message you send might take 1,000,000 years to reach home, and any reply another 1,000,000. By the time you receive it, the society that sent it is long gone. Communication becomes a form of archaeology. You send messages the way ancient structures leave clues, hoping some future intelligence might find them. The relativity-dominated view of travel shows that even without faster-than-light motion, close-to-light speed travel gives travelers a personal experience of crossing enormous distances. It makes the universe feel compressible, but it doesn't make the universe physically small. It doesn't let civilizations stay connected. It doesn't let travelers return to the same world. In a sense, relativity makes intergalactic travel both more possible and more isolating. You can do it, but you leave everything behind, not just in space, but in time. When people hear that reaching other galaxies at realistic speeds would take millions of years, the next thought is almost always, okay, then what about wormholes? What about warp drives? These ideas show up everywhere. Movies, novels, games. And at first glance they seem like clever ways around nature's speed limit. Why crawl across cosmic distances when you can bend or shortcut through space-time itself? The trouble is that once you dig into the physics behind these concepts, you find a pattern. Nothing outright forbids them on paper, But every version we've ever examined pushes into regions of physics where we don't know if nature actually cooperates. And even the versions that don't break the rules come with challenges so extreme that traveling to every galaxy becomes even more impractical than with normal relativistic flight. Let's start with wormholes. In general terms, a wormhole is a tunnel connecting two distant points in space-time. The idea is simple. Instead of traveling the long way through space, you create a shortcut. You go in one mouth of the tunnel, exit the other, and skip the distance between them. In theory, a wormhole could link galaxies, clusters, or even the opposite ends of the universe instantly. No time dilation, no million-year travel times, no cosmic expansion working against you. But the moment you ask, okay, how do we build one? The problems appear. For one, if wormholes exist naturally, they would almost certainly form at scales smaller than atoms, so tiny and unstable that nothing could pass through them before they collapsed. To hold one open, you'd need something that counteracts gravity's tendency to pinch it shut. According to our current equations, the only thing that might do that is a form of negative energy or exotic matter with negative pressure. We don't know if that kind of material exists in usable quantities. We see hints of negative energy at tiny quantum scales, the Casimir effect, for example, but nothing close to the amounts or stability needed. Even if exotic matter exists, you'd need staggering amounts of it. Think of trying to build a bridge across a canyon using materials that behave nothing like anything we've ever seen. And even after building it, you need to keep it stable. Wormholes, if they're possible, would be sensitive to small changes, matter falling in, radiation passing through, temperature variations, and space-time fluctuations. Anything that tries to stretch the geometry too far might collapse the tunnel or create a destructive pulse of energy. Then there's the issue of where the wormhole's exit goes. You don't get to choose where in the universe a natural wormhole opens. If the universe even makes them, their endpoints are likely scattered randomly. So unless you can drag one across space, a task requiring more energy than moving a star, you're stuck with whatever geometry nature gives you. Constructing one from scratch is far more energy-intensive than pushing a ship to relativistic speeds. Even optimistic theoretical papers treat wormhole engineering as an undertaking comparable to manipulating black holes. And speaking of black holes, they offer another question. Could you use them as shortcuts? A rotating black hole has a region inside its event horizon where the geometry might behave like a wormhole throat in certain solutions. But those solutions assume perfect symmetry. The real universe is messy. Any tiny perturbation, falling debris, magnetic fields, even quantum fluctuations, destabilizes the interior. The most realistic models suggest that falling into a black hole destroys you rather than transporting you anywhere. So wormholes aren't ruled out by math, but every workable version demands ingredients that may not exist and engineering far beyond anything conceivable. If humanity someday learns how to manipulate space-time on that level, our understanding of physics would have to leap far past where it stands today. Now consider warp drives. These ideas come from the notion that you can't travel faster than light through space, but maybe you can change the space around you. In the early 1990s, a physicist named Miguel Alcubierre proposed a model where you contract space-time in front of a ship and expand it behind. The ship itself would sit inside a bubble of flat space-time and never move faster than light relative to its bubble. But the bubble could ride a wave of distorted space that moves faster than light relative to the universe. The ship doesn't break relativity because locally, everything behaves normally. It's the space-time wave that moves faster than light. The idea is elegant. In practice, it faces problems as large as wormholes do. The biggest one is, again, exotic matter. The warp bubble requires regions of negative energy to shape space-time the way the equations demand. And to produce a bubble large enough to fit a ship, early estimates showed you'd need more negative energy than the mass energy of the observable universe. Later refinements lowered the requirement dramatically, but still nowhere near anything realistic. Some speculative models claim you can reduce the energy cost even more by changing the geometry of the bubble or using more complex spacetime metrics, but all rely on quantities of exotic energy we've never seen. Another problem is control. Starting or stopping a warp bubble requires conditions outside the bubble, outside the ship. That means you can't control it from inside. You'd need external infrastructure or some way to pre-shape space-time along your route. It's like trying to surf a wave that only appears if someone miles away creates it for you. And if the bubble is moving faster than light relative to the universe, you can't communicate ahead to prepare the path. There's also the issue that a warp bubble might trap radiation at its leading edge. As the bubble travels, it could sweep up photons and particles and compress them into a deadly burst. If the bubble stops, that energy would release all at once. Some models suggest the effect could be catastrophic. Others suggest it could be manageable with clever geometry. But it shows how little we understand about these theoretical constructs. Finally, a warp drive doesn't solve the biggest underlying issue: cosmic expansion. Sure, it lets you outrun light and reach galaxies that would otherwise be unreachable. But the expansion of the universe is relentless, and the farther you go, the more the fabric of space stretches. A warp bubble might let you chase distant galaxies, but beyond a certain distance, even a warp bubble would have to distort space-time more than seems physically reasonable. You could get to many galaxies, but probably not every galaxy. The universe is simply too vast. Even if wormholes or warp drives were possible, building a network connecting every galaxy becomes its own cosmic challenge. A civilization would need infrastructure spanning billions of light years, or it would need to send out self-replicating probes capable of constructing portals or distortions across the universe. Those probes themselves would be limited by the speed of light unless they use shortcuts too, leading to a chicken and egg problem. You need a shortcut to build a shortcut. Without one, you're stuck waiting for construction signals that take millions or billions of years to propagate. Let's imagine just for a moment that some advanced civilization solves these engineering problems. Suppose they understand quantum gravity, manipulate exotic fields, and build stable wormholes or warp networks. Even then, the universe doesn't stand still. Galaxies merge, stars explode, black holes swallow matter and drift. Any fixed address in the universe becomes obsolete. A wormhole mouth anchored to a star system could drift into a different position over millions of years. A warp lane pre-programmed for a particular region might lead somewhere completely different after cosmic structures shift. And then there's the long-term future of the universe. Over trillions of years, star formation will slow down. Galaxies will exhaust their gas. Black holes will merge and evaporate. Cosmic expansion will continue accelerating. Even a civilization with shortcuts might eventually face a universe growing colder, darker, and more diffuse. Some galaxies will slip beyond any possible reach as expansion stretches space faster than any warp or wormhole can counteract. The universe is dynamic, not a static map to be completed. There's also a philosophical angle to all this. When people imagine traveling to every galaxy, they usually picture a grand tour, a ship visiting one after another like scenic stops. But wormholes and warp drives, if they exist at all, don't give you that kind of experience. You don't drift through intergalactic space watching galaxies slide past. You jump from point A to point B in an instant, or ride a space-time bubble that hides the outside universe. The places you see become disjointed snapshots, not a continuous journey. The romance of flying through goes away. You aren't exploring the space between galaxies, you're skipping it. And if a civilization wanted to chart every galaxy, wormholes or warp drives introduce a new complexity: data overload. Each galaxy contains billions of stars. Multiply that by trillions of galaxies, and the amount of information grows beyond any possible storage system. Even if you could reach every galaxy, what would you do with the knowledge? Cataloging becomes impossible. Communication becomes impossible. Synchronizing data across a universe with changing space-time geometry becomes impossible. The act of exploration hits a fundamental bottleneck in the capacity to organize what's discovered. All of this doesn't mean that shortcuts in space-time are impossible. Physics hasn't closed the door, but it has shown that every path toward cheating distance comes with deeper and deeper requirements. Materials we haven't confirmed, energy levels we can't approach, and engineering challenges that look less like technology and more like rewriting the rules of existence. And even if you solve all that, the scale of the universe still pushes back. When you zoom out far enough, the idea of visiting every galaxy stops being a travel plan and becomes a thought experiment that reveals just how enormous the universe is. The laws of physics don't merely make travel hard. They make you confront the fact that most of the universe is permanently out of reach, no matter how clever you get. When we talk about traveling between galaxies, it's tempting to imagine that space is a perfect vacuum, just empty and safe, nothing to hit between the stars. But that's wrong. The space between is deeply hostile. There are subtle but powerful hazards: radiation, high-speed particles, dust and gas, and relativistic effects that turn even the tiniest bit of matter into a deadly threat. The region between galaxies is filled with the intergalactic medium, IgM, a very thin, diffuse plasma of ionized hydrogen and some heavier atoms spread across the cosmic web. Its average density is tiny, on the order of a few hydrogen atoms per cubic meter. That's far, far less dense than interstellar space, which itself is almost a vacuum compared to Earth's air. But very low density doesn't mean harmless, because the distances you travel are so vast, millions or billions of light years. Even a few atoms per cubic meter add up to enormous numbers of impacts. Outside Earth's protective atmosphere and magnetic field, travelers are exposed to high-energy radiation, galactic cosmic rays, GCRs, particles, protons, atomic nuclei, heavy ions, accelerated by supernovae and other cosmic events, and occasional bursts from stellar flares or other energetic phenomena. This radiation is dangerous. It can penetrate shielding, damage DNA, increase cancer risk, harm the central nervous system, and degrade or destroy electronics. For a long voyage, especially intergalactic, the cumulative effects would be huge. What might be manageable on a trip to Mars becomes fatal over thousands or millions of years. If your ship travels at very high fraction of light speed, relativistic speeds, the dangers amplify. Because of velocity, even the sparse atoms in the IgM become hazardous projectiles. At relativistic speeds, collisions with gas atoms, dust, or stray particles deliver massive energy, enough to damage or destroy the hull or irradiate the interior. Dust grains, even tiny ones, and some weights, pose a real threat. A single grain at high speed can vaporize it upon impact, blast away parts of the hull, produce radiation or shock waves. Over millions of years and light years of travel, the bombardment accumulates. The cosmic microwave background and all ambient photons get blue shifted. At high speeds, low-energy background photons become high-energy radiation, adding to the radiation load. One scientific review found that a spacecraft moving relativistically through interstellar/intergalactic medium would suffer continuous damage from particle impacts, radiation, and extreme heating, unless outfitted with very thick, extremely heavy shielding. A protective hull or shield capable of withstanding intergalactic travel would need to absorb or deflect cosmic rays, dust, high-speed atoms, and radiation. One early estimate suggests that to survive certain high-speed journeys, a shield of many meters of dense material, water, metal, or advanced composites might be needed. That much shielding makes the ship very heavy. Heavy ships are harder to accelerate. The energy and propulsion required to push them near light speed become massive, often astronomically impractical. Even though intergalactic space feels empty to us over long distances and long times, that emptiness becomes lethal. Over millions of light years, a ship will pass through enough dust, gas, and radiation to wear out shielding, degrade systems, and endanger any passengers. What might seem like cosmic vacuum is in fact a sparse but dangerous medium. The few atoms and particles, when encountered at relativistic speeds, behave more like bullets than benign emptiness. If you send humans or even sensitive electronics on such voyages, shielding alone isn't enough. Continuous exposure to cosmic rays and ionizing radiation over years or decades can cause radiation sickness, increased cancer risk, impaired immune and nervous systems, organ damage, and severe long-term health effects. Even if the ship is well protected, the shielding system itself might degrade over time under repeated bombardment, cosmic ray showers, and micro-impacts, reducing its effectiveness or failing entirely. Putting it all together, the emptiness, the radiation, the intergalactic medium, and the physics of high-speed travel makes the dream of cruising from galaxy to galaxy far more dangerous than most sci-fi shows. Even if you could build a near-light-speed ship, you'd face a nearly constant barrage of high-energy particles that threaten hull integrity and life support systems. Radiation so intense that shielding becomes impractically heavy. A travel environment where every atom counts and even a single dust grain becomes a potential killer at high velocity. A journey that might be survivable only for unmanned probes. Human crews would need protection orders of magnitude beyond what we can currently engineer. The universe may feel empty and serene when we look at pictures. But if you try to cross even a small fraction of it in a spaceship, that emptiness becomes one of the greatest dangers. Once you accept how harsh intergalactic space really is, an obvious shift happens. Instead of imagining crews traveling from galaxy to galaxy, you start imagining machines doing it. Not clunky robots or probes like the ones we send to Mars, but something engineered specifically for a journey that spans millions of light years, endures constant radiation, and remains functional for time periods longer than most species survive on their home planets. If any tool is going to act as our representative in other galaxies, it won't be a crude ship. It'll be an automated probe built for patience and punishment. Before you picture anything sleek or elegant, it helps to build it from first principles. Start with the simplest requirement. It must survive. That might sound obvious, but survival for millions of years in a hostile environment means something very different from survival for a decade in orbit around Earth. A spacecraft heading into intergalactic space needs to withstand constant micro-impacts, extreme radiation, temperature swings, and the natural decay of materials over huge spans of time. No plastic, no rubber, no degradable electronics, no moving parts that can seize or crack. Everything must be as simple and redundant as possible. And then there's time. Thousands or millions of years of exposure will degrade even the best materials we know. Metals can become brittle. Electronics can be slowly destroyed by cumulative radiation. Power systems fail unless they're constantly maintained. If we send a probe out of the galaxy with the expectation that it still needs to function 10 million years later, we're not really designing a spacecraft. We're designing something closer to a geological object with built-in intelligence. Durability becomes the core element, not speed, not elegance, not complexity. One approach is to minimize complexity. If a probe is meant to travel absurdly long distances, it shouldn't perform delicate tasks that require maintenance. It shouldn't rely on delicate appendages or fine mechanisms. The probe itself would look more like a hardened block, perhaps a dense wedge with a massive shield at the front. The shield is necessary because even a tiny dust grain can be catastrophic if the probe is moving fast. The design doesn't need to be pretty, it just needs to present as little surface area as possible to potential impacts and radiation. But durability alone isn't enough. The probe must also have a plan for power. In intergalactic space, starlight becomes almost non-existent. Solar panels become useless once you leave the neighborhood of your own star. Nuclear power could keep the probe alive for centuries, or maybe a few thousand years, but even those systems decay. If your mission might take millions of years, the power source needs to last longer than anything humanity has ever built. One concept is to put the probe into a kind of hibernation mode, keeping only the most essential circuits active at a bare minimum. It might spend 99.999% of its journey in a deep sleep, waking up only occasionally to check its trajectory or perform simple maintenance cycles. Some have imagined using radioactive isotopes with extremely long half-lives, so the output stays stable for millions of years. Others imagine harvesting energy from the intergalactic medium itself, though the density is so low that any energy you collect this way would be barely more than nothing. You could spend centuries collecting enough power to run a small circuit for a few hours. But if your probe's brain is simple and efficient, that might actually be fine. The journey doesn't demand constant thought, it demands endurance. And then comes the challenge of shielding the probe's electronics. Even if you build them from radiation-resistant materials, they will still deteriorate over time unless you bury them deep inside protective layers. A probe like this almost certainly needs a thick, inert shell, possibly made from metals, alloys, or even new materials engineered to absorb or deflect radiation. Inside that shell, you'd place several redundant computers, each isolated from the others. If one computer fries or corrodes or simply fails, another one wakes up to replace it. Over a million years, redundancy is the only strategy that works. Things will fail, inevitably. You just want the failures to happen slowly and non-catastrophically. But what about propulsion? You can't cross the gulf between galaxies without a plan for acceleration. Carrying fuel inside the probe defeats the purpose. Fuel decays, leaks, or becomes unstable over long storage times. A serious intergalactic probe cannot rely on onboard fuel. The best candidate is external propulsion, either an initial push from a powerful source or a method that doesn't require storing energy at all. One practical idea is a light sail. Instead of carrying fuel, the probe uses a thin, reflective sail pushed by a beam of light from home. You blast it with a powerful laser or other directed energy source for as long as possible, letting it build speed over months or years. Eventually, the beam diverges too much and the probe continues on inertia alone. This isn't speculative. Several real proposals on Earth already use this principle for high-speed travel within the solar system and potentially to nearby stars. It's one of the few propulsion ideas that might actually scale to interstellar or even intergalactic distances. But there are trade-offs. A light sail is fragile. It can tear from impacts with dust or debris, and once it's torn, propulsion stops. For an intergalactic mission, designers would probably jettison the sail after acceleration and rely on a hardened, shielded probe for the rest of the trip. It's a disposable mechanism. You use it once, get your boost, and then discard the fragile parts. Even with that approach, you still face navigation challenges. Over millions of years, trajectories drift. Gravity from galaxies, clusters, and massive structures alters the path. The probe must occasionally adjust its orientation using the smallest possible bursts from tiny, long-lasting thrusters. These could use cold gas, frozen propellant, or electric systems that operate at incredibly slow, steady rates. You don't need much. You just need enough to make slight course corrections every few thousand years. As long as the probe wakes up periodically, checks its star map, and nudges itself in the right direction, it can stay on course. Of course, this assumes you still know where the target galaxy will be. Galaxies move over cosmic timescales. They orbit within larger structures. They merge or drift. To navigate intergalactic space, the probe needs predictions of how galaxies shift. That means the launch civilization must understand cosmic motion over millions of years. It's not impossible. We already track motions of nearby galaxies, but our accuracy drops quickly with distance and time. An extremely long mission might require course corrections based on updated data it receives on the way. And that brings up another problem: communication. A probe millions of light years away cannot easily stay in contact with home. The signal takes millions of years to arrive. Responses take millions of years more. You aren't steering the probe. You're only hoping your message finds a civilization that still exists when it arrives. For all practical purposes, the probe must be autonomous. It decides what to do, where to go, and what counts as a successful outcome. A probe designed for intergalactic travel is more like a tiny, durable explorer than a remote-controlled machine. What would such a probe do when it finally reaches another galaxy? It depends on the mission. Maybe it just takes measurements, maps the structure, samples radiation levels, sends back data about the galaxy's composition or star population. Maybe it deploys smaller subprobes that scatter through the galaxy over millennia. Maybe it steers toward regions that look interesting. Dense, star-forming areas, odd gravitational features, or signs of unusual energy patterns. If you're sending a probe across millions of light years, the analysis must be worth the wait. You wouldn't just want a blurry snapshot, you'd want to know things that can reshape your understanding of the universe. Now imagine building not just one probe, but many. A civilization might send dozens or hundreds of these machines in different directions, like seeds floating into the dark. Over billions of years, some would fail. Some would drift off course. Some would survive and reach other galaxies, then send home data that might return long after the civilization that launched them no longer exists. Communication becomes a message to the future, not a conversation. If the probes were extremely advanced, they might not even need to send data home. They might be designed to replicate. Instead of building one large probe, the civilization builds a master seed probe capable of building new probes using materials it finds along the way. It doesn't need fuel, it just needs time. As it travels, it enters new galaxies, harvests material from dust clouds or asteroids, and constructs offspring. Over cosmic timescales, a probe like this could spread across many galaxies. This idea appears in discussions of von Neumann probes, self-replicating machines capable of exploring the galaxy efficiently. Scale the idea up, and you get a mechanism for exploring the universe. But even with replication, intergalactic distances limit spreading speed. A probe might replicate quickly inside a galaxy, but the journey to the next galaxy still takes millions of years. The universe evolves during that time. Star formation rates change, galaxy shapes drift, expansion continues. Many galaxies move beyond reach. A self-replicating probe won't map the entire universe. It will map a small portion before cosmic expansion carries the rest away. Still, automated machines are the only serious candidates for deep exploration. Humans aren't suited for millions of years of isolation or high radiation. Even with suspended animation, you run into biological decay, genetic damage, and resource depletion. Machines don't care about boredom, radiation exposure, or geological time. They don't age, they don't need food or atmosphere. They can be built to endure conditions humans can't. And yet, even probes face a philosophical limit. They can go out, explore, survive, gather data. But the universe is too vast for any finite number of probes to cover. Most galaxies that exist today are already unreachable because of cosmic expansion. By the time a probe reaches one galaxy, thousands of others will have vanished beyond the horizon. The universe doesn't just sit there waiting, it stretches. This leads to a strange conclusion. The machines humanity sends might one day become part of the universe's long-term structure. They might drift through galaxies long after their creators have disappeared. They might become artifacts future civilizations stumble across, ancient messengers from a species that lived long before. Intergalactic probes aren't just machines, they're time capsules. What these probes represent is the only realistic version of flying through every galaxy. Not a crude adventure, not living beings drifting from one island of stars to the next, but slow, patient machines moving through the universe's structure like spores. If anything will ever touch more than one galaxy, it won't be us. It'll be something built by us, but with a lifespan and endurance so different from ours that it may as well be an independent life form. Leaving a galaxy isn't dramatic. There's no sharp boundary, no wall of stars behind you, and black void ahead. Instead, the number of visible stars thins out slowly, the way city lights fade when you drive out into the countryside at night. If you were looking through a window, the change would feel more like drifting into a quiet region than entering a new type of space. But once you get far enough, hundreds of thousands of light years past the last major clusters of stars, you'd notice a kind of stillness that doesn't exist inside a galaxy. This is intergalactic space, and it's where the scale of things becomes almost hard to process. Inside a galaxy, stars are surprisingly far apart, but you still see many in every direction. Even in regions with few stars, the background glow of the galaxy itself adds a faint light. Outside the galaxy, that glow vanishes. You see something much closer to a raw, untouched universe. The darkness isn't empty, but it feels empty. There's no gas dense enough to see, no dust, no clusters of bright stars forming new generations of systems. For the first time, a traveler would understand why galaxies are compared to islands. The void between them is so vast, you can drift for millions of years without encountering anything larger than a grain of dust. The next thing you'd notice isn't what's around you, it's what the galaxy you left behind looks like now. At first, it would stay bright in the sky because you're still close, but over time it shrinks into a structure with shape, a spiral or an elliptical or some intermediate form. Where it once filled your visual field like an endless band of stars, it would now occupy a small patch of sky with detail you never saw from inside it. You'd finally be able to see its arms, its core, maybe even its satellite galaxies, if it has them. It would feel like looking back at your hometown from high in the air, beautiful, but no longer the world you live in. And as the old galaxy fades behind you, a new one begins to brighten ahead. This approach is the closest thing to flying through every galaxy that physics allows. What makes it interesting is that each galaxy you encounter tells a slightly different story. Galaxies aren't uniform. They evolve, collide, grow, distort, and fade. Your journey becomes a kind of time-lapse tour of how matter arranges itself across cosmic history. The first type of galaxy you might encounter is a classic spiral, something roughly like the Milky Way. Spirals are shaped by rotation and by the behavior of gas clouds that collapse to form stars in organized lanes. From a distance, spirals show clear structure, long curved arms filled with star-forming regions glowing blue. As you get closer, the structure dissolves into countless stars. The bright arms become an illusion produced by density, not literal lines of matter. They're like traffic jams, collections of objects moving along orbits that happen to compress them into recognizable patterns. Flying through a spiral galaxy wouldn't feel chaotic. You wouldn't dodge stars. You wouldn't thread between clusters of glowing gas. Most of the galaxy would feel spacious. Only in dense central regions would the stars appear close together, and even there, the distances are enormous compared to anything familiar to human scale. The core of a spiral is usually a crowded bulge filled with old stars. It's warm-colored, stable, and relatively calm, despite being packed compared to the outer regions. If your journey carried you inward, you'd see the glow of old stars blending together until individual points start to merge into a diffuse light. And at the very center, something waits. A supermassive black hole. You wouldn't get too close. The immediate surroundings of the black hole, the accretion disk, the jets, the hot gas, are dangerous and energetic. But the sphere of influence of the black hole is surprisingly small compared to the size of the galaxy. It acts as an anchor more than a devourer. Moving through the central region, you'd notice the stars orbiting in tight, fast paths. It would feel different from the outer parts of the galaxy, more like the sense of being near a massive object, even if you can't see it directly. After passing through a spiral, you might drift into a type of galaxy shaped by collisions. Collisions happen far more often than most people think, because galaxies are big targets, and space is full of them. These interactions reshape galaxies over millions of years. Some spirals get distorted into long trails, their arms stretched like taffy. Some merge entirely, forming huge elliptical galaxies that look like smooth, glowing spheres with little structure. These are fossil galaxies, collections of stars that no longer form new ones because their gas has been heated or stripped away by past events. Approaching one of these massive ellipticals would be a different experience from approaching a spiral. Spiral galaxies have texture, arms, dust lanes, colourful patches. Ellipticals are diffuse and uniform. They glow like giant clouds made of countless points of red and yellow light. Up close, they lack the dust that gives spirals their dramatic appearance. You wouldn't see dark lanes or glowing nebulae. You'd see mostly old stars, quiet and steady. These galaxies are enormous. Some are so massive they sit at the centers of galaxy clusters, surrounded by thousands of smaller galaxies bound together by gravity. Entering a galaxy cluster is one of the few times the spaceship through the cosmos idea aligns with something visually intense. Clusters contain more galaxies in one region than anywhere else. If you were in the inner parts of a cluster, you might see dozens of galaxies in the sky at once, each with its own shape and size. The gravitational environment would be chaotic at large scales, filaments, flows, interactions, but at your scale it would feel normal. You'd still be in mostly empty space. Clusters are also filled with superheated gas, hot enough to emit X-rays. You wouldn't see it with human eyes, but instruments would show a glowing cloud stretching for millions of light years. This gas isn't dense enough to harm a spacecraft, but it tells a story. Clusters are sites of repeated collisions, mergers, and massive gravitational interactions. They're places where galaxies grow by consuming others. Leaving a cluster and heading toward a more isolated region shows how environment changes galaxies. Some galaxies live alone in quiet parts of space. They evolve slowly. Their shapes stay stable for billions of years. Others live in the cosmic equivalent of a busy highway interchange. They collide, merge, stretch, and transform rapidly. Your journey would reveal that galaxies aren't static. They're more like weather systems, slowly shifting under the forces acting on them. At some point, you'd encounter galaxies that formed early in cosmic history. Younger galaxies tend to be clumpier and messier than the neat spirals we see nearby. Some of them look more like glowing knots than organized objects. Star formation happens everywhere at once, in bursts. If you passed through one, you'd see regions thick with bright, massive stars forming in clusters. These galaxies burn through their gas fast, shining intensely but briefly on cosmic timescales. You might also encounter dwarf galaxies, tiny collections of stars orbiting larger galaxies or drifting alone. They're faint, often irregular, and sometimes so small you could cross them in a fraction of the time it takes to cross a major galaxy. Dwarfs matter because they're the building blocks from which larger galaxies assemble. Our own Milky Way has absorbed many dwarf galaxies in the past, and more are still orbiting it today. A journey across galaxies isn't just a tour of shapes, it's a tour of time. Galaxies closer to us show the universe as it is now. Galaxies farther away show the universe as it was millions or billions of years ago. If you traveled physically instead of looking from Earth, you would see a similar effect, but in reverse. The galaxies you approach would reveal their present state. The ones you passed long ago would reveal their future direction only if you look back. By traveling, you're sampling different evolutionary stages, not because you're looking far away, but because galaxies genuinely occupy different parts of the universe's timeline. Another surprising part of the journey is how dark the universe becomes between galaxies. Even when another galaxy is ahead, you won't see much until you get closer. Galaxies aren't bright from a distance. A spiral galaxy millions of light years away looks like a faint blur, easily overshadowed by even modest light pollution. Only when you're close, within a few 100,000 light years, does its structure become recognizable. Inside galaxies, you'd occasionally cross star-forming regions, giant clouds of gas and dust lit by newborn stars. These are some of the most dynamic regions in the universe. They glow in red and pink tones, full of energetic radiation. Passing near one would reveal walls and filaments of gas shaped by stellar winds and gravity. But they don't last long. Star formation uses up the gas and the cloud eventually disperses. Then there's the opposite environment, the outskirts of galaxies where dark matter dominates. You wouldn't see dark matter directly, but you'd feel its influence through gravity. Stars out here move differently than you'd expect if only visible matter were present. These regions are important because they define the true size of a galaxy. The bright parts are just the center. The actual gravitational structure extends far beyond the glowing disk. What makes crossing multiple galaxies so compelling is how much each one teaches you about how matter arranges itself on large scales. Spirals teach you about rotation and star formation. Ellipticals show what happens when galaxies collide and lose their gas. Dwarfs reveal the earliest building blocks. Clusters demonstrate gravity on enormous scales, and the spaces between them show how the universe expands and stretches over time. If you were somehow able to continue this journey indefinitely, you'd notice a slow trend. Galaxies get farther apart as cosmic expansion accelerates. The ones behind you drift away. The ones ahead move subtly relative to your approach. In the distant future, many galaxies will become isolated islands, permanently cut off from one another. A civilization living in one galaxy might never know others existed unless it inherited ancient data or found evidence from a species that lived earlier when the universe was younger and more connected. This is why describing a journey across galaxies is really describing the universe's lifespan in fast forward. You're seeing objects that themselves are aging, merging, changing shape, or slowly fading. You're moving through a cosmic ecosystem where every structure has a past and a future shaped by physics over billions of years. If you keep following the idea of traveling from galaxy to galaxy far enough into the future, the question stops being, how many galaxies can you reach? And becomes, how many galaxies will even exist in the same universe you started in? That sounds dramatic, but it's simply what the physics points to. Galaxies don't just sit there as permanent landmarks. They age, collide, merge, and eventually fade in ways that reshuffle the entire structure of the cosmos. To get a grip on this, imagine pausing your intergalactic journey and fast-forwarding the universe. Not minutes, not centuries, but billions and trillions of years. Let the clock run until stars burn out. Galaxies reshape themselves, and the large-scale structure of the cosmos evolves into something very different from what you see today. What you discover is that traveling through every galaxy only makes sense in the universe's early chapters. As time marches forward, the number of reachable galaxies shrinks, then collapses to one and finally dissolves into something that barely resembles a galaxy at all. The best place to start is with what's happening right now. Galaxies are still forming new stars. But star formation isn't constant. It peaked billions of years ago when the universe was dense enough that gas clouds collided frequently and cooled efficiently. Since then, galaxies have been slowly using up or losing the gas they depend on to form new stars. Spirals like the Milky Way still produce them, but at a fraction of their earlier rate. Elliptical galaxies barely form new stars at all. Over the next tens of billions of years, this drop continues. The supply runs dry. The galaxies go quiet. If you kept traveling through galaxies during that period, you'd notice a gradual dimming. Young, hot, blue stars vanish first because they burn fuel quickly. What's left are long-lived red and orange stars that glow faintly but for a very long time. A galaxy filled with these looks nothing like the bright spirals we're used to. It becomes calm and reddish, with fewer bright patches and almost no gas clouds to add texture. By the time you're 100 billion years into the future, most galaxies are dominated by these older stars. There's no sparkling, no dramatic nebulae, just long-lasting embers scattered across a huge volume of space. During the same period, galaxies continue to interact and merge. Collisions don't stop just because star formation slows down. Gravity still works. Over time, groups of galaxies pull together, and their motions inside those groups cause them to fall inward and merge into larger structures. If you visited a galaxy group trillions of years from now, it probably wouldn't still be a group. It would likely have condensed into a single enormous elliptical galaxy, a giant pile of stars left behind after all the individual galaxies spiraled together and blended. Our own cosmic neighborhood is heading in that direction. The Milky Way and Andromeda are on track to collide in roughly 4 billion years. Not long after that, the other members of the local group will gradually fall inward too. The eventual result is one supergalaxy containing nearly all the stars in this region. If you were traveling through the universe at that time, you wouldn't see the Milky Way as a separate entity. It wouldn't be something you could visit, it would be one piece of a larger structure, merged into a single object whose shape looks nothing like the spirals we see today. This is where cosmic expansion steps in and changes the picture in a more permanent way. Right now, the universe is expanding, and that expansion is accelerating. The cause appears to be dark energy, something that behaves like a built-in push that makes space stretch faster over time. For traveling between galaxies, this is the real story. While groups of nearby galaxies remain gravitationally bound and eventually merge, galaxies that are far enough away get carried off by expansion. If you try to chase them, you fall behind because the space between you and them grows faster than you can cross it. As time goes on, the number of galaxies still close enough to remain reachable drops exponentially. 1 trillion years from now, almost all galaxies outside your immediate region will have slipped away beyond the cosmic horizon. Even light from them will never reach your position again. The universe becomes a set of isolated islands, separated by distance you cannot cross and signals you cannot receive. If you continued your imaginary journey into that distant era, the concept of flying through every galaxy would no longer make sense. You couldn't reach faraway galaxies even in principle. The only galaxies left in your universe would be the ones gravitationally bound to you, the final, merged mega-galaxy formed from whatever group you began in. Everything else would be gone, not by destruction, but by separation. Expansion would place them permanently outside your observable reality. You wouldn't even be able to tell they were ever there unless someone in your galaxy preserved ancient data from the early universe. Inside your surviving region, the long-term evolution of galaxies becomes the next major chapter. With star formation over, galaxies turn into collections of ever-dimmer objects. Most stars evolve into white dwarfs, hot but tiny remnants that cool slowly. Large stars become neutron stars or black holes. Over huge spans of time, even white dwarfs cool and fade, turning black and cold. Future galaxies won't shine the way present ones do. They'll glow faintly with the remaining heat of stellar corpses and the occasional spark of something unusual, like two white dwarfs merging to briefly produce a new star. But those events get rarer as time moves forward. If your journey continued into far future trillions of years, you'd start to notice that the galaxy is losing mass. Not rapidly, just slowly, one star at a time. Interactions fling objects out of the galaxy. Black holes absorb some matter. A small number of stars get ejected into intergalactic space. Over time, the galaxy becomes less tightly bound. Eventually, even the merged megagalaxy can disintegrate if enough mass is lost. The result is a sky where stars fade one by one as they cool into black, invisible spheres. Then there are black holes. These are the last major gravitational objects to evaporate. Hawking radiation, which lets black holes lose mass very slowly, takes enormous timescales to matter, on the order of 10 to the 60 to 10 to the 100 years, depending on the size of the black hole. But if we fast forward far enough, even these giants shrink and vanish, leaving behind only radiation. If your imaginary journey pressed on through these eras, you wouldn't be crossing galaxies anymore. The structures would be gone. You'd be moving through a space filled with cold matter and particle remnants. The patterns that once defined galaxies, spirals, ellipticals, clusters, fade into the background. Space becomes extremely quiet. No new stars form, no bright galaxies remain. What you'd see is closer to a cosmic shadow of what once existed. At this point, the universe is no longer a place where flying through galaxies has meaning. Galaxies aren't stable features anymore. They're historical moments. The bright, structured universe you see today is temporary. It exists in the slice of time where stars shine, gas clouds glow, and galaxies show off their shapes. Before this era, there were no galaxies. Long after this era, there won't be any left to travel through. Even if you zoom in closer and think only about your local cosmic region, the outcome is the same. Galaxies merge into one. That structure dims, it slowly dissolves. Black holes evaporate. The remaining particles spread apart as expansion continues. Eventually, distances become so enormous that the universe is functionally empty. If you were still traveling, somehow maintaining enough energy to keep going, you wouldn't encounter galaxies, stars, or even warm dust. Everything that once formed galaxies would be cold and isolated. This doesn't make the present universe any less remarkable. In fact, it makes it more so. The era where galaxies exist is a small window in cosmic history. The idea of traveling through them is only meaningful within this narrow band of time. If you step far enough into the future, even conceptually, you're moving through a universe where exploring galaxies is impossible because galaxies themselves are temporary. And so when you imagine flying through every galaxy, you're really imagining flying through a specific moment in the universe's timeline. One where the structures we recognize are still here, still bright, and still shaped by the physics that created them billions of years ago. If you pull back far enough, galaxies look less like permanent landmarks and more like evolving clouds that eventually drift apart and fade. If you imagine your long journey continuing into the distant future, past the era of star formation, past the merging of galaxies, past the cooling of stellar remnants, you eventually arrive in a version of the universe that doesn't resemble the one we know at all. The word galaxy stops being useful because the structures themselves have faded, broken apart, or stretched into something too diffuse to recognize. But this doesn't mean the universe becomes simple. It just becomes different. The physics that shaped galaxies for billions of years gives way to slower processes that dominate the universe when everything bright has gone quiet. A universe without galaxies begins with a slow transition. The first change isn't the disappearance of stars, it's the disappearance of the patterns that made galaxies interesting. Spirals lose their structure as star formation ends. Ellipticals stop glowing brightly as their stars age. Clusters thin out as galaxies merge into one. If you were traveling during this phase, the differences from today wouldn't hit you instantly. The process is subtle. Each galaxy just looks a little older, a little dimmer, a little less structured than the last one you passed. But the trend is steady. Over billions of years, even the largest galaxies settle into diffuse balls of fading light. Eventually, the brightest stars are gone. Only smaller, longer-lived stars remain: orange dwarfs, red dwarfs, and white dwarfs. These stars shine for trillions of years, much longer than the universe has existed so far. If you were inside one of these ancient galaxies, the night sky would look sparse. Deep red or orange stars would dot the darkness, but the overall glow would be faint. You wouldn't see familiar bands of bright starlight. Nebulae with their dramatic colors would be gone. Starbirth would be over. But the biggest change comes when even those long-lived stars begin to die. Red dwarfs burn extremely slowly, but eventually they exhaust their fuel. White dwarfs cool until they radiate almost no visible light. One by one, they fade from view. By this stage of your journey, galaxies no longer have bright centers or glowing edges. They're filled with stellar fossils, cold, dark spheres left behind from earlier eras. If you crossed one of these future galaxies, it wouldn't feel like flying through a galaxy at all. You'd be moving through a volume of space that's nearly invisible, containing objects that only reveal themselves by blocking your instruments for a moment as they pass in front of background radiation. Gravity would still be there, but light would not. You'd be navigating through a place held together by mass, but offering almost no visual cues about where that mass is located. The next major change is slow, but it reshapes everything. Gravitational interactions begin breaking the last megagalaxies apart. Although galaxies are gravitationally bound, they're not closed systems. Over trillions of years, small interactions add up. Stars and remnants pass close enough to one another to exchange energy. Some get accelerated and escape into intergalactic space. Others fall inward and get consumed by black holes. The result is a gradual thinning of the galaxy. It doesn't collapse or explode, it just becomes less dense and less structured over astonishing lengths of time. You'd see this as a galaxy that stretches out and fades from the inside. No bright core, no organized shape, just a wide cloud of almost invisible mass. Traveling through it would be like drifting through the ghost of a galaxy rather than the real thing. This slow unbinding continues until the last gravitational relationships dissolve. What used to be a galaxy becomes a scattering of remnants spread across enormous distances. At that point, structures we once recognized disappear. The universe doesn't have galaxies, clusters, or anything that resembles the formations we see today. It has isolated objects drifting through expanding space. Black holes become the final defining features of this era. For a long time, they remain the most massive and compact things around. If you're traveling through this future, the only landmarks left are these black holes, once at the centers of galaxies, now floating through nearly empty space. They still bend light, they still warp gravity, they still mark where galaxies used to be. They almost feel like megascale fossils, the cores of ancient structures that no longer exist. But even black holes aren't eternal. Over inconceivably long periods, they slowly lose mass through Hawking radiation. The larger the black hole, the longer this takes, but none of them last forever. Some survive for 10 to the 60 years. The largest could last for 10 to the 100 years. Those numbers are so large that comparing them to the current age of the universe, 13.8 billion years, barely means anything. But if your journey extended that far into the future, you'd eventually witness the last black holes shrinking, glowing with increasingly faint energy, and finally evaporating. Once the black holes are gone, something strange happens. The universe stops having places. Everything left is widely distributed particles, mostly electrons, positrons, neutrinos, photons, and whatever dark matter might still be around. There isn't a meaningful sense of structure. There's no center, no clusters, no bright objects. Space becomes a thin fog of particles drifting farther apart as expansion continues to accelerate. If your ship was somehow still operating, the environment would be almost featureless. There would be no galaxies to navigate toward, no landmarks to fly past, no gravitational wells large enough to form new structures. Space would be cold and nearly perfectly uniform. The difference between being in one place or another becomes almost meaningless because the universe has become smooth. A natural question comes up here. Does any physics still matter in a universe like this? Surprisingly, yes. It just changes focus. First, the quantum properties of particles still matter. Even in a nearly empty universe, particle interactions continue, though at extremely low rates. You'd still detect the faint background radiation from earlier eras. You'd still have to consider the occasional rare interaction between remaining particles. Second, dark energy continues to drive expansion. As space expands faster and faster, the distances between isolated particles grow until they surpass any scale we can easily imagine. The universe doesn't become static, it keeps changing, but in a way that spreads matter more thinly with time, rather than clumping it. Third, entropy keeps increasing. This is the guiding rule of the late universe. Everything trends toward maximum entropy, the state where energy is spread as evenly as possible and little can happen. That's why structures disappear and why nothing new forms to replace them. Fourth, the geometry of the universe still evolves. Even in the absence of galaxies, the shape and expansion behavior of space-time continue to matter. Physicists sometimes refer to this last era as the heat death, because the universe reaches a point where useful energy is so diluted that no organized process can happen. It's quiet, smooth, and dominated by expansion. Now imagine trying to continue your journey in this environment. There's nothing left to travel to. Moving forward or backward is just moving into more of the same. The idea of visiting galaxies becomes as outdated as the idea of crossing continents in a world where continents no longer exist. Your ship wouldn't be a traveler anymore, it would be drifting in a universe where meaningfully different locations don't exist. But here's an interesting twist. If your ship somehow carried a complete record of the universe's history, maps, data, simulations, It would become the last source of structured information in a universe that has forgotten everything. The ship itself becomes the final artifact of cosmic complexity. Even if the universe fades around you, the data you carry holds patterns that no longer exist anywhere else. In a strange way, your craft becomes the last galaxy in the sense that it contains the last organized forms of information. This future universe doesn't erase its past. It just stops preserving it physically. Only memory remains, and memory is something a traveler can carry, even when the sky goes dark. Which raises the final point of this section. Flying through galaxies is not just a journey across space, it's a journey across the life cycle of the universe. It starts in a place filled with bright stars, gas clouds, and dramatic structures. It ends in a place where the universe's history is something you bring with you, not something you can find by exploring. When most people imagine traveling through the universe, they picture it like a giant cosmic map, a place with destinations you can mark, regions you can cross, and objects you can approach the way you might visit countries on a globe. That mental model works for short distances. Short meaning a few million light years. But once you zoom out far enough, once you start thinking about billions or trillions of years and trillions of galaxies, the map becomes misleading. The universe is not just a layout of places, it's a story that unfolds. If you try to visit everything in it, you eventually realize you're not traveling through space, you're traveling through time. This shift in perspective becomes unavoidable as soon as you start comparing distances to cosmic timescales. Even the simple idea of going to the next galaxy immediately throws you into the past. Galaxies aren't just far away, they're separated in time because of how long light needs to reach you. By the time you're close enough to see one clearly, you're already looking at it in a different era than when you left your previous one. Space is so stretched out that moving from one galaxy to another means jumping between ancient snapshots of cosmic history. Think about what that means in practice. When you start your journey in the Milky Way, you're seeing everything around you in real time. Stars form, explode, collide, and orbit as they do today. But the moment you accelerate toward another galaxy, even at extreme speeds, you're already stepping backward through the universe's timeline. You see that galaxy not as it is now, but as it was millions or billions of years earlier. And when you finally reach it, the light you saw on approach is no longer relevant. The galaxy has aged. It's changed. You're behind the image you saw on the way in, so visiting every galaxy becomes something like flipping through pages of a book while walking across a massive library. You don't just move from one shelf to another. You watch the story shift as you go. The galaxies you pass early in your trip exist in the same cosmic chapter as the Milky Way. But the farther you go, the more each new destination places you deeper in the universe's past. The trip stops being a tour of locations and becomes a tour of eras. This also means that the phrase "every galaxy gets messy." Which version of a galaxy counts as the real one? The galaxy as it appears from afar, still young, still forming stars? Or the galaxy as it actually is when you get there, maybe older, dimmer, or partially merged with others? You can't visit both. You can only visit one physical state of it. The light you saw from far away is a historical document, not the place itself. In the early parts of your journey, you might approach spirals that look bright and structured from millions of light years out, only to arrive and find a very different galaxy. One that's lost gas, lost structure, or collided with a neighbor. The longer your journey goes on, the larger that gap becomes. Your travel time also interacts with cosmic expansion in a way that makes the idea of every galaxy even stranger. Early on, you're limited by distance. Later, you're limited by the fact that many galaxies recede from you faster than you can reach them. That means your list of reachable galaxies actually shrinks as you go. Even if you traveled forever, the universe expands faster than you can move across it. Visiting everything becomes impossible, not because of technology, but because of the shape of space-time itself. The more you travel, the more unreachable galaxies slip past the horizon. The universe essentially edits your list for you. But there's another layer. Galaxies evolve internally while you're traveling. They don't wait for you. A galaxy you pass early in your trip won't look the same when you're millions of years away from it. By the time you reach another cluster, entire populations of stars have lived and died behind you. In a cosmic sense, traveling doesn't let you experience different parts of the universe simultaneously. It lays them out in a sequence. Your perspective is always shaped by where you've been, how fast you're going, and when you arrive. This turns the entire concept of flying through the universe into something closer to observing the life cycle of a living organism. Galaxies aren't just scattered objects, they're stages of development. Some are young and chaotic, some are in their calm middle age, some are in decline. A traveler moving fast enough for long enough becomes a witness to how galaxies age more than a visitor of individual locations. You see early, messy starburst galaxies in one part of the journey and encounter a cluster dominated by old elliptical giants in another. You're seeing snapshots of cosmic evolution laid out in space, but really tied together by time. The more of the universe you cross, the more obvious this becomes. The early parts of your trip might feel like exploring a huge and varied neighborhood. Spiral galaxies here, dwarf galaxies there, star-forming regions glowing all around. But as you continue, patterns emerge. You start to notice how many galaxies share similar shapes at similar stages. You see how the availability of gas controls whether galaxies form new stars or fade. You see how interactions carve their shapes, how gravity sculpts their motion, how dark matter anchors their structure. You aren't just seeing distant objects, you're learning the universe's habits. And that brings something unexpected. After long enough, individual galaxies stop standing out. What you remember instead are transitions, moments when the universe changes flavor, when the density of galaxies around you rises, when clusters first appear, when clusters give way to superclusters, when cosmic filaments dominate the landscape, when the voids open up. Your mind shifts from cataloging galaxies to tracking patterns. The same way a biologist eventually stops thinking about individual trees and starts seeing entire ecosystems, you start seeing the universe as a set of structures that grow, interact, dissolve, and evolve. This shift also changes how you understand isolation. At the beginning of your journey, the Milky Way doesn't feel isolated at all. You can see the local group. You can see nearby clusters. You can see the large-scale structure of the universe glowing in every direction. But the farther you get, the more you realize how much of the universe is empty. Not empty in the sense of boring, but empty in the sense of giving the objects within it room to grow and drift. Galaxies don't dominate the universe. The void does. Flying toward a new cluster can feel like approaching an island across a vast ocean. After a while, you may start to wonder whether galaxies are the exceptions and the emptiness is the rule. Once you start thinking in these terms, every galaxy starts to sound like saying you want to see every wave in the ocean. Waves aren't permanent. They don't exist apart from the sea. Galaxies are the same way. They are temporary arrangements of matter created by the universe's conditions at particular eras. They are constantly changing and eventually they disappear. Seeing them all doesn't mean ticking off a checklist. It means understanding how the conditions that make galaxies possible evolve over cosmic time. This is also when the emotional tone of the journey changes. Early on, galaxies feel like destinations. Bright, complex, full of interesting physics. Later, they feel more like artifacts of a younger universe. You begin to sense that the universe is shifting under your feet, moving away from the era of bright objects and toward an era dominated by slow processes. The entire universe becomes a timeline that you're moving along whether you intend to or not. Eventually, you start to realize the significance of your own vantage point. A stationary observer in a single galaxy doesn't see this unfolding. They see only their era. But a traveler crossing the cosmos sees the universe aging in a way no single location ever can. You aren't just exploring geographic distance. You're experiencing the universe's arrow of time firsthand. You watch as the most active periods of star formation fade away behind you. You watch as the large-scale structure becomes more diffuse. You watch as the accelerating expansion changes, which galaxies remain reachable and which slide out of view forever. Your travel becomes a record of cosmic evolution. The universe you started in is not the universe you end up in. Not because you moved far away, but because time has marched on. At some point, you may begin to realize that even if you could somehow jump instantly between galaxies, the concept of every galaxy would still be impossible. Galaxies aren't static targets. They're moving, merging, fading, and transforming. Many of them will cease to exist long before you reach them. Others won't form until long after you've passed their future location. In other words, there is no single universe full of galaxies waiting to be visited. The universe is changing too continuously for that. What you're really visiting is a sequence of stages, each one giving you a different view of what galaxies are at that moment in cosmic time. That's the deeper shift. Travel turns the universe from a map into a timeline. At the start of a journey like this, exploration feels straightforward. You point your ship at a distant galaxy, fire up whatever propulsion you've mastered, and go. It's a bigger version of crossing an ocean or a continent. More distance, harder obstacles, stranger hazards, but the same core idea. Move from one place to another and learn something new along the way. But after long enough, that idea starts to unravel. The scale of the universe doesn't just stretch distance, it stretches meaning. The farther you travel, the more the concept of exploration shifts from covering territory to understanding transitions. At some point, you're no longer exploring places. You're exploring conditions. You're watching how a universe evolves when nothing stays fixed for long enough to treat as a stable destination. A traveler early in the journey might feel like an adventurer. A traveler halfway through becomes a historian. A traveler later on becomes something closer to an archivist, someone who carries context with them because the universe stops providing it externally. This shift doesn't happen all at once. It creeps in slowly, starting with the way distance interacts with time. When you cross a few million light years, the galaxy you arrive at is different from the galaxy you saw before you left. The delay is tiny compared to the galaxy's age, but it's non-zero. Then you cross a few 100 million light years, and the difference is clearer. Whole generations of stars have come and gone during your travel. Nebulae have dispersed or condensed. Spiral arms have shifted. The galaxy you studied on approach doesn't match the galaxy you enter. You can't escape this. The universe keeps aging whether you're moving or not, and that forces you to rethink what it means to explore. You're not exploring fixed objects, you're exploring processes. At first, this is exciting. You get to watch galaxy evolution play out in real time, something no stationary observer could ever see. After a few billion years of travel, you have a mental catalogue of how galaxies age that no simulation could replace. You've seen the early chaotic ones with wild starburst regions. You've seen the stable spirals. You've seen the quiet ellipticals that barely change anymore. You can practically identify a galaxy's age group from a single glance at its shape and behavior. But the excitement eventually turns into something more reflective. You start thinking about what you're really trying to accomplish. If the universe is constantly changing, and if enormous portions of it are drifting permanently out of reach, what does it mean to explore all of it? At what point does exploration stop being a mission and start being a way to understand your place in an environment that's too large and too dynamic for ownership or completion? There's a moment most travelers would eventually reach, an internal tipping point where the universe stops feeling like a frontier and starts feeling like a companion that's slowly aging alongside you. You stop imagining the universe as a set of targets and start experiencing it as a living timeline, with each new region showing you how far along that timeline you've moved. Think of what happens when you enter your first truly massive cluster. Early in your journey, clusters might feel like destinations, densely packed, radiant, full of interacting galaxies. But 1 trillion years later, when star formation has slowed across the universe, clusters feel different. They're no longer busy. They're heavy, stable, almost contemplative structures. A cluster that once glowed with new stars becomes a quiet shelter of aging galaxies orbiting each other in graceful, predictable paths. The once chaotic collisions slow down. The bright, messy, spectacular era of galaxy interaction fades into long periods of calm. Then you leave the cluster, travel for millions of years through open space, and arrive in a region where star formation ended even earlier. The galaxies you find there are older, dimmer, and less structured. The differences between regions become differences in evolutionary stage. Your journey becomes a record of those changes, a timeline written across billions of light years instead of billions of years. The idea of exploration keeps shifting the deeper you go. It stops being about discovery and starts being about witnessing. You're not mapping new territory, you're documenting where the universe is in its life cycle. You're piecing together how everything fits into the larger arc of cosmic history. In a strange way, you become a historian for a universe that can't preserve its own past. That's one of the hidden truths about traveling far enough across space. You eventually outlive cosmic landmarks. Not physically, you don't outlive stars or galaxies, but you outlive the consistency of their identities. A galaxy you catalogue early in your journey might merge with another long before you could return. The bright regions that first caught your eye could fade. The shape that made the galaxy memorable might dissolve. You carry memories of a universe that no longer exists behind you, and those memories become the only permanent archive of those eras. It's a slow realization, but a powerful one. Exploration makes you a repository of context. You become the link between epochs that would otherwise have no connection. This becomes even more pronounced as cosmic expansion accelerates. Early on, the horizon of reachable galaxies is broad. A good fraction of the universe is within theoretical reach. But as time goes on, more and more galaxies drift away faster than you could ever catch them. The universe isn't just expanding, it's erasing paths behind itself. The list of places you could visit shrinks every million years. If exploration once felt like expanding your reach, now it feels like trying to preserve access to what's left. And that raises a strange emotional tension. Your journey gives you extraordinary breadth of experience, far more than any fixed observer, but the universe constantly narrows your future options. You have to decide what exploration means in a reality where the frontier recedes faster than you can chase it. Do you focus on the galaxies still within reach? Do you slow down and study them deeply, knowing that they're among the last you'll ever see? Do you keep moving in order to stretch out the timeline of discovery as far as possible? There isn't a universal answer. Exploration becomes personal. It becomes about what you value in a universe that's transitioning towards silence. Some travelers, if such travelers existed, might focus on finding the last pockets of active star formation. Others might seek out dense clusters long after most galaxies have become quiet. Others might decide to study the structure of dark matter as visible matter fades. Some might gravitate toward black holes, the final titans of gravity, long after every bright system has gone dark. But the deeper truth is that exploration becomes less about collecting experiences and more about witnessing the end of eras. You're not trying to see it all anymore. You're trying to understand what it means for the universe to age, to change, to shed complexity over time. This gives your journey a kind of narrative arc that isn't about distance at all. It becomes about what the universe was and what it's becoming. You started in a universe full of brightness and complexity. You move through one where galaxies mature, stop forming stars, merge and stabilize. You eventually enter an era where light grows scarce, where only old stars remain, where remnants dominate, where black holes outshine everything else, simply by the energy they emit as they consume matter or slowly evaporate. And eventually you travel into an era where even black holes are fading. Exploration becomes a meditation on impermanence, not in a poetic way, but in a physical, measurable sense. You're watching entropy reshape everything. You're watching the fundamental rules of energy distribution slowly erase structure, just as they were always destined to do. And yet, despite all that, the journey remains meaningful because you're the one preserving continuity. The universe loses its past as it evolves, but you don't. Moving across vast distances gives you access to snapshots millions or billions of years apart. Moving across vast times gives you personal experience of those snapshots changing. The combination makes you a witness to something no fixed observer could ever see. The universe as a sequence, not a place. By the time galaxies are few and far between, your memories hold more structure than the universe itself. That's the final evolution of exploration. You're no longer cataloguing new places. You're preserving the memory of how the universe once looked when it still had the complexity we take for granted today. Exploration becomes meaningfully finite, not because the universe is small, but because the universe itself is always changing faster than you can chase its earlier forms. You start to understand that seeing every galaxy was never the real goal. The real goal was understanding what galaxies represent, temporary arrangements of matter shaped by conditions that themselves change over cosmic time. The deeper you travel, the more this becomes obvious. Exploration isn't about finding objects. It's about learning the rules behind their existence and the rules behind their disappearance. By the time your journey stretches into the far future, well past the eras when galaxies are bright, well past the periods when new stars still form, the universe has changed enough that your role in it changes too. You started as an explorer, but eventually the universe strips that role away. Not harshly, but gradually, the same way a coastline erodes over centuries. You're not exploring a landscape anymore. You're outliving the structures that once defined it. The last bright galaxies fade behind you. The great clusters thin out. Black holes become the only major landmarks left, and even they grow quiet over enormous spans of time. Traveling between these objects starts to feel like moving through the afterglow of something that used to be lively. The universe hasn't become empty, but it has grown quiet in a way that feels unmistakably final. This shift forces you to rethink identity. What does it mean to be a traveler in a universe where destinations barely exist? What does it mean to have memories of a cosmos that no longer resembles what you see around you? Very slowly, you become something the early universe never needed, a keeper of continuity. Traveling long enough makes you a witness to transitions that nothing in the universe was built to preserve. Galaxies don't remember what they used to look like. Stars don't remember what they used to orbit. Even the large-scale structure forgets its own early patterns as expansion stretches everything apart. But you do. You carry the Milky Way with you long after it stops being recognizable. You recall the shape of clusters that later dissolve. You remember the way bright spiral arms once filled the universe with patterns that feel almost impossible in the far future's darkness. Your memories are snapshots of existence the universe itself no longer contains. That's when your purpose shifts again. You stop thinking of yourself as a traveler who moves from place to place. You become a traveler who moves from era to era. Space stops being what defines your experience. Time does. You're the only continuous thread passing through chapters that would otherwise be isolated from each other. If someone asked you why you still travel at this point, you wouldn't say it's for discovery. There's very little left that's new in the conventional sense. You'd say you travel because it lets you see how the universe handles its own ending. Not in a catastrophic sense, but in a slow, natural, unavoidable one. Watching entropy strip away structure doesn't feel dramatic. It feels like watching an ancient process complete itself. As the universe approaches heat death, distances become almost meaningless. There are no bright objects to travel toward. Black holes slowly shrink through Hawking radiation, losing mass bit by bit. Once they vanish, even gravity stops offering you landmarks. Matter thins out into a sparse distribution of particles with no structures left to reorganize. The universe becomes smooth, and that smoothness brings a new kind of clarity. Without external structure, your memories become the richest patterns left. You're carrying the universe's history in the same way a library carries the memory of civilizations that no longer exist. Even if nothing around you is changing anymore in any obvious way, what you've already seen gives you context that the present universe simply doesn't provide. The traveler becomes the structure. In the younger universe, galaxies defined meaning. In the older universe, your perspective defines meaning. It's not ego, just simple physics. Complexity fades everywhere except inside the mind of the one thing still capable of storing it. This realization can feel heavy or peaceful, depending on how you look at it. In one sense, you become uniquely alone. Not lonely necessarily, but singular. No stars, no nebulae, no clusters can speak for themselves anymore. You're the last witness to the universe's bright chapters. In another sense, the journey becomes more meaningful than ever. The farther you travel, the more you understand why earlier eras looked the way they did. You've seen how the conditions changed. You've seen how galaxies aged and disappeared. You've seen dark energy reshape what counts as reachable. You've experienced cosmic evolution as no single galaxy, no single epoch ever could. In a way, the traveler becomes the final point where the universe's story is coherent. Not because you're special, but because only a moving observer can stitch the eras together. You're the thread passing through a tapestry that otherwise unravels. Eventually, even motion becomes abstract. With no structures left, there's no practical difference between being here or there. Expansion carries everything apart at scales so large that direction loses meaning. Exploration becomes quiet reflection. You're not searching for anything, you're just continuing the timeline. And that brings you to the last transformation. The traveler becomes the historian of existence. Your journey started with the idea of visiting every galaxy. But galaxies were only the opening chapter. What you really did was witness the life cycle of the universe itself, from the era of bright matter to the era with almost none. The universe no longer remembers itself, but you do. There comes a point in this journey where the universe stops changing in ways you can meaningfully observe. Not all at once, and not with any dramatic signal, just slowly, gradually, until the silence becomes unmistakable. Black holes evaporate one by one. Particles thin out. Temperature differences flatten. Light from earlier eras stretches to wavelengths so long that even your instruments struggle to detect them. You're still moving, but nothing around you reacts to your movement. Space feels less like a landscape and more like a background state. Reaching this stage isn't like crossing a boundary, it's more like noticing that the last remaining sources of change are inside your own memory, rather than out in the universe. When you look outward, every direction gives you the same faint, uniform glow of stretched-out radiation. When you look inward, you see the entire history of galaxies, clusters, mergers, starbirth and star death stretched out behind you. The contrast becomes so sharp that exploration no longer describes what you're doing. You're not uncovering new information, you're carrying the last of it. Travel starts feeling less like motion and more like preservation. With no destinations left and no structures to navigate by, your path is defined only by time. Each moment nudges you further into the universe's quietest era. And because nothing external changes quickly anymore, time starts to feel different. Earlier in your journey, millions of years passed without you noticing, because galaxies always offered something new. Spiral arms shifting, star-forming regions glowing, collisions reshaping the sky. Now, even trillions of years can pass without any visible difference outside your ship. Your role shifts again. You're not a traveler, you're not an observer. You become the last system in the universe that can still hold on to complexity. The universe around you moves toward maximum entropy, perfect spread-outness, perfect uniformity. Meanwhile, you're the one object left that still contains organized information. Everything you've seen, every era you've crossed, every memory you carry is structure the universe has lost everywhere else. At this point, you might feel a strange responsibility, not imposed, just natural. The universe can't record its own past anymore. Temperature differences have flattened too much for any physical imprint to last. But your memory still carries the shape of things. You remember the local group before it merged. You remember the first clusters you visited. You remember the lights of galaxies that disappeared billions of years earlier. You remember eras the universe has completely erased around you. In the same way fossils preserve the history of Earth, long after the creatures themselves have vanished, you preserve the shapes and patterns of the cosmos long after the galaxies themselves have dissolved. What you do with those memories is up to you, but the universe won't take them back. They exist only in you now. Eventually, the last black hole vanishes. When that happens, something subtle but profound shifts. For the first time since the universe began, gravity is no longer organizing matter on large scales. There are no compact objects left. No stars, no remnants, no clusters, just particles drifting apart in a sea that gets thinner and colder without limit. At this point, there's truly nothing to arrive at, no structures to encounter, no geometry that changes on any practical timescale. Motion becomes indistinguishable from stillness. Even concepts like direction start to lose meaning when the universe is so uniform that every path looks identical. But your memories remain structured. They give you orientation even when space doesn't. They give you a sense of before and after. They give you a sense of identity. Without them, the universe would simply be smooth, featureless, and forgetful. With them, at least internally, the universe still has chapters. Eventually, you reach the last meaningful question of your journey. What does it mean to continue in a universe where there is nothing left to find? Some travelers might say the journey ends here, not physically, but conceptually. They might choose to slow down, conserve energy, and simply exist in the fading quiet. Others might choose to keep moving, not because they expect anything ahead, but because motion is part of who they have become. Momentum becomes identity. Continuing becomes a way of honoring the universe's earlier eras, the eras where movement mattered. And some would see meaning in carrying the record itself. The universe no longer forms memories. You do. The journey becomes a kind of stewardship. You hold onto the story of everything that has happened, even when the universe can no longer tell that story on its own. In a younger universe, traveling across galaxies was about scale. In this universe, at the end of all structure, traveling becomes about meaning. The universe gave you its brightest chapters early in your journey. You carry the final chapters yourself. There is no final destination because the universe no longer offers destinations. But there is a final perspective, a traveler who has seen the universe not just spatially, but chronologically, someone who understands not only where galaxies once were, but what they meant in the context of the universe's life cycle. The journey ends not with arrival, but with understanding. When the universe has reached its quietest state, when no stars shine and no galaxies remain, you're left with something that doesn't exist anywhere else anymore, the memory of a universe that once had structure. And that memory becomes the last source of light in a cosmos where physical light has stretched beyond usefulness. Long after the last black hole evaporates, the universe settles into a state where change slows to a crawl. There are still particles, still fields, still the geometry of space-time, but nothing forms new structures. Nothing collapses. Nothing ignites. All the dramatic eras, the formation of the first stars, the building of galaxies, the rise of clusters, the great mergers, the long twilight of stellar remnants, those are gone. The universe has reached a kind of final equilibrium. In this era, your memories become a contrast so sharp that they feel almost unreal compared to the smooth background outside. You remember brightness in a universe where brightness no longer exists. You remember shape and contrast in a universe that has none. You remember complexity after the universe has given up every power it once had to create it. That memory isn't just sentimental, it's physical. Information is structure. As long as you retain organized memories, you are, at least locally, lower entropy than the space around you. It won't last forever, but for a while you remain the last coherent archive of the universe's history. Travel still happens, but it no longer changes anything. You move through space that no longer has destinations. You move through eras that no longer have distinctions. The universe isn't pushing you anywhere and you aren't chasing anything. You're just continuing, carrying a record that the universe itself has erased everywhere else. There's a calmness to this part of the journey. Early on, you were surrounded by objects so bright and dynamic that you couldn't help but feel small. Now, you are the only structure left with any meaningful complexity. Everything outside is uniform. Everything inside is layered with the echoes of a universe that lived a long, complicated life. You might decide to store your memories in whatever durable form you can. Maybe that's internal, maybe that's external, a record etched into whatever medium can survive longest in a universe where even atoms will eventually decay. The point is no longer to be read or discovered. The point is simply to exist long enough to honor the cosmos that once was. Even that eventually will fade. Every system runs down. Memory degrades. Organized information spreads out. Heat death catches everything, even the last archive. But the value of the journey isn't in its permanency. It's in the fact that you experienced the universe across its full arc. You saw the beginning of structure, the height of it, the slow winding down of it, and the final quiet after it. For a universe that cannot remember itself, a traveler like you becomes its last witness. And that's where the story ends. Not with a discovery, not with a destination, but with a perspective. You carried the universe's brightest eras into its darkest one. You became the final connection between what the universe once was and what it eventually became, long after the galaxies you visited dissolved into silence. Imagine starting a journey with one simple goal: fly through every galaxy in the universe. At first, it sounds like an adventure built on scale. An impossible road trip, sure, but still a road trip. You picture countless islands of stars scattered across space, each one waiting to be visited. But as soon as you take the first step, the idea changes. You're not just moving through distance, you're moving through time, evolution, and eras of the cosmos that unfold on scales far larger than anything we experience on Earth. By the time you grasp what every galaxy really means, you're already deep into a journey that has turned into something completely different from what you expected. The first question you run into is simple. How many galaxies are there? For a long time, astronomers estimated about 100 or 200 billion. That already sounded overwhelming until deeper surveys pushed the number far higher. The current estimate lands around 2 trillion galaxies in the observable universe. The key word is observable. That's just what light has had time to reach us from. Beyond that boundary, space continues, possibly with trillions more galaxies we'll never see. Even sticking to the observable part, you're dealing with a quantity so huge that it reshapes your entire idea of scale. But it isn't just the number of galaxies that matters. It's the space between them. Even the closest large galaxy, Andromeda, is about 2.5 million light-years away. That's the distance light travels in millions of years. Most galaxies are much farther than that, so if you imagine this as a journey where you hop from one galaxy to the next, you spend almost all your time not near galaxies at all, but drifting through silent, thin intergalactic space. You cross long stretches where nothing happens. No stars pass by, and the nearest light looks like a faint smear behind dust and gas. On top of that, the universe is expanding. On small scales, like inside a galaxy, you don't notice it. Gravity holds everything together. But between galaxies, especially ones far apart, space stretches. The farther away a galaxy is, the faster it seems to move away from you as the universe expands. Go far enough and the expansion outruns even light. Those galaxies slip beyond a horizon you can never cross. No matter how fast you travel, the universe is expanding faster. As cosmic acceleration continues, more galaxies leave reach forever. So even at the very start, you discover that every galaxy already excludes most of the universe. They're gone. Not destroyed, just inaccessible, carried away faster than you or light can follow. But suppose you keep going anyway. You aim for the galaxies that still can be reached. You travel unimaginably far, and you give yourself all the time you need. As you move from one galaxy to the next, you start seeing patterns. Galaxies are not random points. They cluster into groups, and groups into clusters, and clusters into enormous filaments that stretch across the universe. And between those filaments are enormous voids, regions where almost nothing exists. Crossing a void can take longer than crossing the full diameter of a dense cluster. In each galaxy you visit early in your journey, stars are still forming. You'll see bright blue, star-forming regions, glowing nebulae, supernova remnants, and dense clouds collapsing under their own gravity. But this part of the universe's life doesn't last forever. Star formation slows down. Gas is consumed and blown away. Over time, galaxies become quieter. They shift from blue and active to red and passive. The universe burns through its fuel. Long before you reach even a tiny fraction of the reachable galaxies, entire classes of galaxies begin changing. Small galaxies merge into larger ones. Large galaxies cannibalize their satellites. You'll see titanic collisions that reshape their cores, spawn waves of new stars, and eventually settle into calmer shapes. If you keep traveling for hundreds of billions of years, you'll witness a deeper shift. Galaxies within the same gravitationally bound region merge into a single megastructure. For us, the Milky Way, Andromeda, and dozens of smaller galaxies will eventually merge into one giant elliptical galaxy. This won't be a rare event. It becomes the final stage for most bound groups. After that, each cluster or group becomes a single blended object, drifting alone. As the universe ages, your journey becomes less varied. Star formation slows as gas becomes scarce. The bright blue era of the cosmos gives way to one dominated by long-lived red and orange stars. Over trillions of years, even those will burn through their fuel. The galaxies you visit later in your timeline won't look like anything you'd recognize from the early universe. They'll be made mostly of dead stars, white dwarfs, neutron stars, and black holes. You'll still see motion and structure, but the glow of young stars won't be there to light your path. Eventually, the universe moves past the era where stars shine at all. White dwarfs cool. Neutron stars drift in the dark. Black holes dominate the scenery. Entire galaxies, once filled with billions of luminous stars, become dim collections of remnants orbiting a central black hole. The contrast between early stops on your journey and these later ones becomes sharper than anything you could imagine. It's like visiting vibrant, crowded cities at the beginning and abandoned, silent ruins at the end. Except the scale is trillions of times larger. As you keep traveling, you reach a stage where black holes begin to evaporate. This is a process predicted by quantum physics. Over enormous time spans, black holes lose mass through Hawking radiation. For supermassive black holes, this takes far longer than current cosmic time. But given trillions upon trillions of years, even the largest black holes shrink and vanish. If you're traveling through the universe at this stage, you'll see the last powerful gravitational engines blink out one by one. Once the final black hole evaporates, the universe enters a new era. There are no stars, no remnants with heat, no dense regions that create interesting structure. Matter is spread thin. Space becomes extremely uniform. You still move, but there's nothing to navigate by. No bright spots, no clusters, no cosmic landmarks. It's like sailing an ocean where all waves are flattened and the water stretches perfectly evenly in every direction. This is when you realize something profound. You're no longer exploring. There is nothing left to find. You've outlasted the structures that once gave the universe shape. What remains outside your ship changes so slowly that billions of years pass without noticeable difference. The universe becomes a background, not a landscape, but there's something that sets you apart from everything else. You still remember. You remember the bright era of galaxies. You remember starbirth. You remember the colors, the collisions, the variety, the organized complexity. The universe around you can no longer store those memories in any physical form. There are no surfaces that can hold patterns, no gravitational structures, no temperature differences that can encode information. But you contain the last organized record of what once existed. Your memories become the final contrast in a universe that has gone flat. They are the last low-entropy pockets in a space that drifts toward perfect uniformity. You hold the shapes of galaxies long after galaxies themselves are gone. In a very real sense, you become the universe's final witness. Eventually, even your systems will decay. Memory won't last forever, but the significance isn't in lasting forever. It's in the fact that you carried the universe's full arc inside you. At the beginning, the goal was to fly through every galaxy. By the end, the journey became something else. You didn't just visit galaxies, you outlived them. You didn't just see the universe, you saw it change. You became a thread connecting eras that the universe itself no longer remembers. The journey ends not because you reach a final destination, but because the universe has no new destinations left to offer. What remains is perspective. You witnessed a cosmos from its most vibrant era to its quietest one, and you carried its story into a time when nothing else could. Subscribe.